Imagine a darkness so complete that the very idea of dark loses all meaning, a state beyond absence, beyond time, beyond space, beyond even the potential for anything to be. And then, in an instant that defies even the concept of time, something exploded into being. You are witnessing the birth of everything, the moment when from absolute nothingness, all that ever was and ever will be emerged in a single, indescribable act of creation. But what exactly is nothing? This deceptively simple question has tormented philosophers and physicists for millennia. To Aristotle, nature abhorred a vacuum. To ancient atomists like Democritus, emptiness was merely the space between indivisible particles. Medieval scholastics debated whether God could create a true void. Yet modern physics reveals that even what we once called a vacuum is not truly empty. Quantum field theory tells us that even the most perfect vacuum teems with energy fluctuations, virtual particles flashing into and out of existence in an eternal quantum dance. It is not stillness, but a chaotic sea of potential. Let's reimagine nothingness as the absence not only of matter but of laws, geometry, causality, everything. Such a nothing would be unstable, because there would be no principles to prevent something from emerging. And if emergence is possible, it becomes inevitable. A universe might not just arise, it must arise. What if our universe is one such anomaly? An improbable quantum ripple that gained permanence. In 1927, Werner Heisenberg formulated the uncertainty principle, a fundamental rule of quantum mechanics, stating that certain pairs of properties, like a particle's position and momentum, cannot both be precisely known. This principle ensures that even a vacuum must contain some irreducible energy, known as zero-point energy. This energy ripples as fluctuations in space-time itself, manifesting as virtual particles. Though ephemeral and unobservable directly, their presence is betrayed by real effects, like the Casimir effect. When two uncharged metal plates are placed closely together in a vacuum, quantum fluctuations create a pressure that nudges them together. Space, it seems, is never truly empty. In this quantum world, everything not forbidden is compulsory. Virtual particles blink in and out of existence by the trillions, constantly. But what if, one day, a fluctuation failed to vanish? Some models suggest that a fluctuation of sufficient energy could become stable, expanding rapidly and giving birth to an entire universe. This is where the theory of cosmic inflation enters. In a fraction of a second, space itself expanded at a rate faster than the speed of light. All the energy in a pinpoint ballooned into the cosmos we see today. The Big Bang was not an explosion within space, but of space. Approximately 13.8 billion years ago, all that we know was packed into a singularity smaller than an atom. The temperature was so extreme that particles could not yet form. But then, in a moment less than a billionth of a second long, inflation occurred, expanding space itself by a factor of more than 100,000. This smoothed out the universe, explaining its astonishing uniformity. When inflation ceased, energy condensed into matter and antimatter. For reasons we do not fully understand, matter won by a razor-thin margin of 1 particle per billion. Without that imbalance, the universe would be nothing but light. In the first 3 minutes, the universe cooled enough for protons and neutrons to form the nuclei of light elements, hydrogen, helium, a touch of lithium. But atoms could not yet form. For 380,000 years, light was trapped in a fog of charged particles. Then came recombination. Electrons settled into orbits around nuclei, forming the first atoms. The universe became transparent. Light, once caged, was free. That ancient light still surrounds us, the cosmic microwave background. A fossil glow from creation itself. What came before the Big Bang? That question may be meaningless. If time began with the Big Bang, then before is not a valid concept, like asking what lies north of the North Pole. Yet some theories suggest precursors to the Big Bang. Perhaps our universe emerged from a quantum fluctuation in a larger multiverse, or from the collapse of a previous universe, or the collision of higher dimensional brains. In the 1920s, Edwin Hubble discovered that the universe is expanding, but in 1998, astronomers made a startling discovery that expansion is accelerating. Distant supernovae appeared dimmer than expected, suggesting they are farther away, pushed not just by initial momentum, but by an unknown force. We call it dark energy. It now appears to make up about 68% of the universe, and its nature is a profound mystery. It might be the energy of the vacuum itself, a cosmological constant that Einstein once inserted into his equations and later regretted. Or it could be something else entirely: quintessence, a dynamic field that changes over time, or a clue that our understanding of gravity is incomplete. This dark energy governs the fate of everything. If its repulsion remains constant or grows, galaxies will drift ever farther apart. In the distant future, cosmic expansion will accelerate until galaxies vanish beyond visibility. In one scenario, the Big Rip, this expansion could eventually overcome all forces, tearing apart stars, atoms, even space-time itself. But perhaps our universe is not alone. According to some theories, countless other universes may exist in a multiverse. Eternal inflation suggests that while inflation ended in our region, it continues elsewhere, spawning new bubble universes with differing physical laws. In quantum mechanics, the many worlds interpretation posits that every quantum choice splits reality, forming new branches. There are also mathematical multiverses. Max Tegmark proposes that every consistent mathematical structure corresponds to a physical universe. The fine-tuning of physical constants lends credence to the multiverse idea. Why are the laws of physics just right to allow atoms, stars, life? In a multiverse of endless variation, we happen to live in a universe that permits observers because otherwise, we wouldn't be here to ask. String theory seeks to unify all known forces by describing particles as different vibrational modes of tiny one-dimensional strings. These strings are unimaginably small, far beyond our current ability to observe. For consistency, string theory requires extra dimensions beyond the familiar four. These extra dimensions are thought to be curled up in complex geometries called Calabi-Yau manifolds, invisible to us but crucial to the laws of physics we observe. Loop quantum gravity offers a different vision. Instead of continuous space-time, it proposes a fabric woven from discrete loops. Space and time emerge from quantum geometry. In this view, gravity is not a force but a manifestation of the curvature of this network. According to some models, our universe may have emerged from a quantum bounce, a prior universe collapsing before rebounding into expansion. Then comes the holographic principle, born from the study of black holes. Stephen Hawking and Jacob Bekenstein showed that a black hole's entropy and thus its information content scales with its surface area, not its volume. This led to a radical proposal: our 3D universe could be a projection of information encoded on a distant 2D boundary. Space and time, in this view, may not be fundamental, but emergent from quantum information and entanglement. Why is the universe so finely tuned for life? Why do constants like the strength of gravity or the mass of the electron have just the right values? One answer is the anthropic principle. We observe these values because only in a universe with such properties could observers arise. In a multiverse, most universes would be lifeless. We live in one that isn't, because otherwise we wouldn't be here. Could consciousness itself play a role in the universe's origin? In quantum mechanics, observation seems to collapse possibilities into realities. Some interpretations suggest that consciousness might play a part in this collapse. Ideas like the participatory anthropic principle propose that the universe requires observers to exist. Perhaps, in some deep way, the universe and consciousness are entangled, two aspects of the same fundamental reality. Mathematics underpins the universe so precisely that some propose the cosmos is a mathematical object. Max Tegmark's mathematical universe hypothesis posits that reality is not just described by math, it is math. Every consistent mathematical structure exists, and ours is one that supports life. In this view, creation is not something that happened in time, it is the realization of mathematical possibility. Yet, even mathematics has limits. Kurt Gödel's incompleteness theorems prove that any mathematical system will have true statements that cannot be proven within it. If the universe is mathematical, then some truths about it may be forever beyond our grasp. Quantum uncertainty, the speed of light, the cosmic horizon all impose boundaries on what we can know. At the frontier of science lie the philosophical questions. Is the universe necessary or contingent? Is it deterministic or governed by chance? Is consciousness a byproduct or a fundamental property of reality? Perhaps the universe is not merely a set of particles and fields, but a process of becoming a dynamic interplay of energy, geometry, information, and awareness. And so, our journey through cosmology leads not only outward but inward. We are the cosmos contemplating itself. Born from stardust, shaped by quantum fluctuations. Driven by curiosity, we reach back across eons to understand the spark from which everything arose. Perhaps we will never know the full answer to how something emerged from nothing. But in asking the question, we affirm our place in the story of existence. Begin with a silence deeper than stillness, a moment suspended beyond the reach of time, where space itself has not yet dreamed of existing. No forms, no boundaries, not even a void to occupy. Then, a rupture, not a sound, not a flash, but a shift in potential, an eventless event, the quantum awakening from which everything will spill. This is not the Big Bang. This is what allows it. What follows is an explosion not of matter, but of being. The birth of distance, direction, dimension. Energy condenses into form as time takes its first breath. Space inflates, expanding faster than any light it will ever host. This brief, furious surge, cosmic inflation, writes imperfection into the fabric of reality. Tiny quantum irregularities, magnified by the storm, become the seeds of all future structure. Where the void once reigned, possibility now pulses. From that inconceivable flash, a superheated plasma emerges, a primordial broth of quarks, leptons, photons. The universe is less than a second old, and already, its laws are defining themselves. Quarks swarm and combine, forming protons and neutrons. Antimatter appears as their mirror, only to vanish in mutual annihilation. Yet the symmetry breaks for every billion collisions. One particle of matter survives. This narrow margin, this sliver of survival, becomes the foundation of galaxies and dreams. The first 3 minutes stretch the canvas further. Helium and hydrogen nuclei are forged, along with whispers of lithium. The lightest elements in the periodic table take their place, marking the beginning of chemical identity. But atoms remain elusive. Electrons wander free, scattering every photon into a haze. For hundreds of thousands of years, light cannot move forward, until it does. The universe cools, electrons bond with nuclei, and the cosmos clears. In that moment, a veil is lifted. Photons are set free, carrying with them the imprint of their long imprisonment. That afterglow, the cosmic microwave background, remains our most ancient message from the cosmos, a fossil of the universe's transparency. Yet in this newborn clarity, darkness returns. No stars, no galaxies, only hydrogen and helium adrift in vast silence. These are the cosmic dark ages, where gravity plays its long game. The imperfections born in inflation now whisper to matter, drawing it together. Slowly, clouds of gas condense, mass folds upon mass, heat builds, atoms crash, and then, ignition. The first stars blaze into existence. Titans of fusion, short-lived and massive. They forge heavier elements in their cores and scatter them into space when they die. Their light ends the dark ages, rayonizing the universe, making it transparent not just to light, but to future possibility. These stars are ancestors not just to galaxies, but to every molecule of your body. Their deaths are spectacular supernovae that hurl matter across light years, neutron stars that spin like cosmic lighthouses, and perhaps, in the most extreme cases, black holes that bend space-time into wells of silence. Each event becomes part of the universe's unfolding story, creating structure from chaos, complexity from collapse. The building blocks of life are being cast in fire. Carbon, nitrogen, oxygen. These elements emerge not from chemistry, but from the thermonuclear alchemy of stars. The periodic table becomes a kind of stellar memory, a ledger of what the universe has dared to create. Galaxies gather under gravity's spell, spiraling into forms that echo the chaos of their birth. Some will merge, collide, and devour. Others will drift in majestic isolation. Each one is a library of light, its stars recording time with nuclear rhythm. They pulse, flicker, explode, die, and in doing so, teach us. Within these islands of light, planets begin to form. Disks of dust and gas swirl around infant stars, colliding and coalescing. Rocky worlds and gas giants emerge. Some fall into their suns. Others are flung into the interstellar void. But just a few, find the balance that allows oceans to pool, atmospheres to cling, chemistry to stir. From this, life may rise, but that is another story. This is how the cosmos lays its groundwork. Through fluctuation, imbalance, and fire. Through decay and recombination. Through gravity's relentless hand. It is a story still without voice, still without thought, but not without intent. The script has been written. The players are assembling. And far from the future consciousness that will one day gaze backward and wonder, the universe continues to unfold, unaware of its own grandeur. The lens of the James Webb Space Telescope gathers a whisper from the past, a luminous thread from a galaxy whose light has traveled over 13 billion years to reach us. This single signal, faint and redshifted, carries not only photons but the weight of epochs, of stars that lived and died long before our solar system even dreamed of forming. It marks the beginning of a new cosmic chapter, the age of galaxies. From the chaotic fire of primordial stars, gravity stitched the universe into structure. Where once only isolated points of light flickered, now vast galactic assemblies emerge, each a cathedral of 100 billion stars, wrapped in dust, gas, and the subtle framework of dark matter. These structures, fragile in the vastness, are nonetheless bound together by gravity's invisible hand, forming filaments across space like neural pathways of a thinking cosmos. They are not randomly placed, but patterned, clustered into superstructures and separated by immense voids, like breaths between stanzas of a cosmic poem. The early galaxies were unruly things, misshapen, blazing with starbirth, often colliding with each other in balletic violence. Such mergers weren't catastrophes, but acts of creation. As galaxies collided, clouds of gas compressed, triggering new generations of stars. Over billions of years, these frantic forms matured into spirals and ellipticals, elegant systems like our Milky Way, which itself formed from the union of smaller galaxies. But the true architect of these formations is a presence we cannot see: dark matter. It exerts no light, no heat, no signature detectable by ordinary instruments. Yet its gravitational influence is everywhere. It sculpts the universe's large-scale structure, provides scaffolding for galaxy formation, and dictates the motion of stars far from galactic centers. Without dark matter, galaxies would fly apart. It is the silent partner in every celestial dance. Beneath this grand choreography lies the process of star and planet formation. Stars, born from cold molecular clouds, ignite in clusters, their ultraviolet light carving cavities into the very wombs from which they formed. Around many young stars, protoplanetary disks swirl a theater of dust and gas, chaotic and creative. Here, particles stick, clump, grow. Planetesimals emerge, then protoplanets. Over time, through collisions both violent and delicate, solar systems take shape, moons are captured, atmospheres are sculpted, water often delivered by comets and asteroids settles in cold basins. Some planets will become frozen wastelands, others smothered in acid clouds. But a few, with the right chemistry and distance from their star, will enter the narrow zone where liquid water can exist, the habitable zone. Our Earth is one such world, but it is not unique. Over the past 2 decades, astronomers have cataloged thousands of exoplanets, many of them Earth-sized and located in habitable zones. Some orbit stars smaller and redder than the Sun, where a year lasts mere days. Others circle twin stars, like a scene from science fiction. The diversity is staggering, and it reshapes our sense of what is typical. Earth may be special to us, but it is likely not rare. The more we observe, the more we find that the cosmos is biased toward complexity. Given enough time, molecules organize into patterns, amino acids form chains, lipids assemble into membranes, autocatalytic cycles arise. On Earth, this pathway led to the emergence of cells, self-replicating structures that would evolve over billions of years into fungi, fish, forests, and finally, minds that ponder the stars. What sparked the transition from chemistry to biology is still unclear. Perhaps life began in hydrothermal vents at the ocean's bottom, where heat and minerals created the perfect crucible. Or maybe it started in shallow tidal pools under the sun's gentle light. Some scientists even propose panspermia, that the seeds of life arrived on Earth aboard comets or meteorites, born in the chemistry of other worlds. Wherever it began, life on Earth remained single-celled for most of its history. For over 3 billion years, microbes ruled, transforming the atmosphere, shaping minerals, and building microbial mats that still exist today. Only recently, in the last half-billion years, did multicellular life explode in diversity. Cambrian seas teemed with trilobites, anomalocarids, and the first vertebrates. Plants crept onto land, followed by insects, then reptiles, birds, mammals. But consciousness, true, reflective awareness, may be as rare as it is profound. It is a phenomenon not just of neurons firing, but of memory, language, abstraction. Somewhere along the way, a primate species in East Africa began to ask questions that no other animal had ever asked. What is out there? Where did we come from? Are we alone? We now use radio telescopes to scan the sky for signals not made by nature. We send robotic emissaries to other planets, seeking biosignatures, chemical hints of life. And we build instruments so sensitive they can read the faint fingerprints of alien atmospheres. Yet so far, we have heard nothing. The universe, for all its noise, remains silent. This silence is haunting. It births the Fermi paradox, the tension between the high probability of alien life and the lack of evidence. Maybe intelligent life is incredibly rare, or self-destructive. Maybe civilizations exist, but stay quiet. Or perhaps we are too early. The first sparks in a still dark cosmos. Each possibility carries philosophical weight. Still, we listen. Still, we search. For in that search is a reflection of ourselves, not just our desire to find others, but our need to understand our place in the vast design. We are shaped by the same forces that sculpted galaxies, built from atoms forged in stellar hearts. And now, we look back across billions of years, reading light that began its journey before our planet even existed. Begin with a pulse, a whisper of hydrogen collapsing under its own gravity, deeper into a furnace it cannot escape. In the heart of stars, the simplest element is forged into helium, releasing light and heat. This cycle of fusion, of fire turned to form, continues for billions of years. But even stars exhaust their fuel. When they die, they do so spectacularly, some in silence, others in apocalyptic detonations. In these violent deaths, new elements are born: carbon, oxygen, silicon, iron. A supernova is not an ending. It is a chemical declaration. The remnants of these stellar deaths drift through space, seeding clouds that will one day form new stars, new worlds. Every atom in your body heavier than hydrogen, every calcium ion in your bones, every iron atom in your blood was born in a star that died long before Earth formed. We are not just stardust, we are star aftermath. From these elements, over cosmic time, complexity re-emerges. On worlds like Earth, molecules combine into cells, cells into organisms, and some organisms into minds that ask why. With every evolutionary step, memory becomes more sophisticated, awareness more nuanced. The brain, a dense lattice of neurons, constructs internal models of the external world. Time, language, emotion, and abstraction arise not from magic, but from matter in motion. Yet consciousness remains enigmatic. Is it merely computation, or is it something more? Some theories suggest that consciousness may emerge from specific patterns of information integration. Others propose that it reflects quantum coherence within neural networks. But no theory yet fully explains how subjective experience arises from physical systems. This is the hard problem of consciousness, not just how the brain processes information, but how it feels like something to be a brain. If we extend this enigma into the cosmos, we begin to wonder, could consciousness be more than an accident? Might it be a fundamental feature of reality, like mass or charge? Panpsychism suggests that all matter has a rudimentary form of awareness. Integrated information theory proposes that consciousness arises from complexity wherever it occurs. Under such views, The cosmos doesn't merely host minds, it may itself be part mind. But to what end? Why would a universe give rise to creatures who can contemplate it? This question touches on the anthropic principle, the observation that the universe's laws seem finely tuned for the emergence of life. Change the strength of gravity, the charge of an electron, or the expansion rate of the universe even slightly, and atoms wouldn't hold, stars wouldn't ignite, planets wouldn't coalesce. Life as we know it would be impossible. One response is selection bias. We observe a life-permitting universe because only such a universe could contain observers. Another is the multiverse if countless universes exist, each with different physical constants. We find ourselves in one that supports life because we couldn't exist in any other. But there remains a haunting third option, that our universe is not just permitted, but intended. This doesn't imply design in a theological sense, but invites speculation. Could the universe be algorithmic, self-organizing, or even simulated? The simulation hypothesis, once confined to science fiction, now finds foothold in cosmology and computation. If advanced civilizations could simulate entire realities, and if such simulations outnumber base realities, then statistically, we are more likely to be in a simulation than the original universe. Yet even if true, this changes nothing about the awe we feel. A simulated universe is no less majestic. Its stars still shine, its laws still govern, and our feelings, our questions, our search for meaning remain authentic. In this light, the story of the universe becomes the story of emergence from quarks to consciousness, from randomness to reflection. Complexity blooms in pockets, then networks, then minds. Information flows like a river through the ages, from the Big Bang to Bach, from neutron stars to novels. Every layer of reality builds upon the last. Entropy, the tendency of systems to become more disordered, defines the direction of time. Yet within this descent, islands of order arise, galaxies, cells, civilizations, all are structures that delay entropy by exporting disorder elsewhere. Life exists not in spite of entropy, but because of it. It is a thermodynamic improvisation, a rebellion within constraint, and time itself. Time is not a river but a construct, a mapping of events onto entropy's arrow. To us, it feels linear, but in physics, especially in relativity, time can dilate, stretch, even loop. The past and future are woven into the present by our perception. Memory gives direction, anticipation gives shape. Without consciousness, time would have no meaning. So we return to where we began, not at the Big Bang, but at the mystery behind it. Why is there something rather than nothing? Perhaps there was never nothing. Perhaps nothingness was unstable. Or perhaps, in some unknowable equation, the emergence of a cosmos and the emergence of minds to witness it are bound together. We are not the center of the universe, but we are its mirror. In us, it contemplates itself. In our sleep, it dreams. And in our questions, it awakens. Let this idea settle, like stardust on a windowsill. Let it drift with you into the hush of sleep. In a desert observatory under a velvet sky, a radio dish turns silently toward the stars. A signal has arrived, sharp, unexpected, narrowband. It lasts 72 seconds. Then silence. This was 1977, the now famous wow signal. We still don't know what caused it. Perhaps it was noise. Perhaps a satellite, but perhaps not. The uncertainty remains a symbol of our search, not for certainty, but for the glimmer of contact. That longing for connection, for pattern, runs through the whole human story. We map the sky, name constellations, and write myth into the stars. But myth becomes model, and model becomes method. We now peer beyond our galaxy, detect gravitational waves from colliding black holes, measure ripples in the cosmic microwave background, and infer planets from the wobbles of distant suns. Yet the more we learn, the stranger the cosmos becomes. There are galaxies rotating faster than they should, clusters moving as if pulled by unseen forces. The cosmic microwave background holds unexplained cold spots. Even the distribution of matter hints at symmetries and voids that defy our models. We call these cosmic anomalies not errors, but messages from a deeper layer of reality we do not yet understand. Dark matter and dark energy are the twin mysteries. Together, they make up 95% of the universe. Yet we have never directly seen either. We detect dark matter through its gravitational influence, and dark energy through the accelerating expansion of space. But what they are, particles, fields, or failures of our equations, remains unknown. It's as if we're trying to understand an ocean by studying the foam, and yet, our minds are built for patterns. So we hypothesize, simulate, test. We build particle colliders to probe the smallest scales and telescopes to scan the largest. Some physicists explore supersymmetry or extra dimensions. Others revisit gravity itself, asking if general relativity is the whole story. And a few dream of a theory of everything, an elegant equation that unites quantum mechanics and gravity, matter and mind. But perhaps the final answer is not an equation. Perhaps it is a question, or a paradox. What if our universe is one of many? The multiverse is not just speculation. It arises naturally from inflation theory, string theory, and even quantum mechanics. Each universe might obey different physical laws, contain different constants, host different outcomes. If true, our universe is not the stage, but a stage one of countless performances. Yet within this stage, the drama continues. Stars still burn, planets still spin, life still rises. Civilizations build tools, write songs, send spacecraft across the void, and with time, they face their own challenges. Climate, entropy, catastrophe. The future, like the cosmos, is wide open. Will we endure? Will we reach other stars or fall inward? Will artificial intelligence surpass our biology and become the next layer of cosmic awareness? Will we find other minds or become the ancestors of minds yet unimagined? And what is the ultimate fate of it all? Cosmologists imagine several endings. The heat death, where expansion continues forever and entropy erases all gradients, stars die. Black holes evaporate, and the universe becomes a thin, cold fog of particles. Or the Big Crunch, where expansion reverses and all matter collapses. Or the Big Rip, where dark energy grows stronger, pulling galaxies, stars, atoms, even space-time itself apart. Each possibility reflects not only physics, but metaphysics. But perhaps the end is not an end. Perhaps the universe reboots, collapsing and bouncing, birthing a new cosmos from the ashes of the last. Or perhaps it never ends, not in time, but in story. For as long as there are minds to wonder, to ask, to imagine, there is meaning.
The very concept of a beginning for the universe forces us to confront one of the greatest and most profound mysteries in all of human history. What, if anything, existed before the Big Bang? Understanding the birth of our cosmos is not just an exercise in revealing the deep past. It is a journey that sheds light on our present reality and illuminates the possible futures that lie ahead. This single, profound question has driven scientists for generations to explore the furthest reaches of cosmological mystery, leading to the development of numerous and often competing theories that help us to piece together the grand narrative of the universe's evolution. However, the moment that preceded the beginning, the instant before time and space as we know them came into existence, remains a vast and tantalizing unknown, a frontier of discovery that pushes the very limits of our science and our imagination. The enigmatic presence of dark matter and dark energy, the unseen components that dominate our universe, are further shaping and reshaping our understanding of the fundamental nature of reality. What happened in that unknown period before the Big Bang is not just a question for physicists. It is critical to understanding humanity's true place in the cosmos and the ultimate direction of our collective evolution. Now, we will journey to the very edge of that great question, exploring the theories, the paradoxes, and the profound philosophical implications of the universe's origin. The very concept of time is, for us, the fundamental way in which our consciousness and the physical events of our lives are organized. It is the river on which we float, a constant and seemingly absolute flow from a fixed past to an open future. However, scientifically speaking, Time itself may have had a beginning, a moment of birth that coincided with the birth of the universe. According to Albert Einstein's theory of general relativity, time is not a separate, independent entity, but is inextricably intertwined with the three dimensions of space into a single, dynamic fabric known as space-time. The beginning of this intricate and beautiful intertwining is the event we call the Big Bang. This idea, that time and space were born together, could render the very concept of before the Big Bang meaningless, as the word before itself requires the existence of a temporal dimension in which to have meaning. It is like asking what is north of the North Pole. The question itself is built on a framework that ceases to exist at that point. Nevertheless, some compelling and sophisticated theories suggest that time, in some form, may have existed before the birth of our particular universe. For example, cyclical universe models, which have deep roots in both ancient philosophy and modern cosmology, assume that time flows not in a straight line, but in an infinite loop. In these models, the universe undergoes endless cycles of expansion, collapse, and rebirth. In this case, the beginning of our universe would be an illusion, just one turn in an eternal cosmic wheel, and time would continue to exist, in some form, through every cycle. Quantum cosmology theories, on the other hand, offer an even more strange and counterintuitive picture. They argue that time does not have a classical, definitive beginning, but rather that quantum fluctuations transitioned from a timeless, probabilistic state to the familiar, one-dimensional arrow of time that we experience today. This suggests that a kind of proto-time, an immeasurable and non-linear form of existence, may have existed before time as we know it began. Therefore, the profound question, what existed before the beginning of time, is one of the most challenging and mind-bending questions we can ask. A question that straddles the line between science and philosophy. Perhaps the answer lies forever beyond our current understanding of time, in a higher dimensional reality or an entirely different plane of existence that our minds are not equipped to comprehend. Where was the universe before the Big Bang? This question, which seems so simple and so natural, is actually one of the most fundamental and misleading questions we can ask about the nature of space and time. To ask where the Big Bang took place is to assume that there was a pre-existing place, an empty stage on which the cosmic drama unfolded. However, according to our best understanding from modern cosmology, the universe did not happen in a place. The universe created all places. Time and space were born together at the moment of the Big Bang. Therefore, the universe was not in any particular location, because location itself did not yet exist. To think that there was a void, a volume, or an empty space before the universe is a product of our classical, everyday logic, a logic that is built on our experience of a world where things happen within a pre-existing arena. But the origin of the universe challenges the very boundaries of this classical logic. Since space itself was created at that moment, the question of where it was before may not make any logical sense. It is like asking what is outside the surface of a sphere. The surface of a sphere is a finite, two-dimensional space that is complete within itself. There is no outside to it. Alternative theories, however, do offer some intriguing models that give a new context to this question. Theories of a multiverse, or the concept of brain cosmology, suggest that our universe may be just one component, one brain or membrane, existing within a larger, higher dimensional space that contains other universes. In these approaches, our universe may have been born from a collision with another universe, or from a fluctuation within this larger bulk space. In this case, there may indeed have been another plane of existence, another kind of place, before our universe began. Thus, the question, where was it, becomes an investigation into the nature of the cosmic environment in which our universe was born. Ultimately, The question of where the universe was before the Big Bang is not only a physical problem but also a linguistic and philosophical one. It is not the position of the universe that should be questioned, but its very existence. Because before the Big Bang, according to our standard model, there was neither space nor position. What existed before the universe? This question forces us to confront the deeply perplexing concept of nothingness directly. To ask what existed before the universe is to try to understand the absolute boundary between existence and non-existence. Scientists cannot, at present, definitively know whether there was a state of true physical nothingness before our universe came into being. This is because our observational evidence, the light from the most distant galaxies, and the cosmic microwave background, can only take us back to the very first moments of the universe's existence, but not to the moment of creation itself. According to some scientific models, particularly those emerging from quantum cosmology, before our universe existed, there may have been a pure quantum field, a state that is often described as a quantum vacuum. This field may have contained a vast amount of potential energy, which could have then, through a random quantum fluctuation, initiated the birth of the universe. This kind of nothingness is not absolute emptiness. It is a quantum nothingness, a state where the familiar laws of classical physics do not operate, but where the potential for existence is still present. Philosophically, the question "what was there before the universe?" forces us to confront one of the most fundamental questions of all. Why is there something rather than nothing? This is a question that philosophers have been trying to answer for centuries, and it lies at the very heart of metaphysics. The answer may lie in the radical idea that nothingness itself is not a natural or stable state. Perhaps existence is the default, the natural state of being, and the universe is simply the inevitable result of the potential that is inherent in reality. In short, it is still a matter of intense debate whether there was ever a time when the universe did not exist. Perhaps the universe, in some form, has always existed. It has simply changed its form over an infinite amount of time. Or perhaps it really did come into existence from nothing. But this nothing was a state of non-existence that is profoundly different from the simple emptiness that we can imagine. At first glance, the concept of nothingness seems to be a very simple one. It is a state in which nothing exists. It is the void, the abyss, the absolute absence of all things. However, upon closer and more careful examination, this seemingly simple concept is revealed to be deeply and profoundly problematic. In the world of physics, the term nothingness usually refers to a vacuum, which is classically defined as a region of space that contains no energy or matter. However, modern physics, and particularly quantum mechanics, has shown us that even this physical vacuum is not actually empty. Quantum field theory states that the vacuum is a seething, roiling sea of activity, where pairs of virtual particles and antiparticles are constantly and spontaneously forming and then annihilating each other in a fleeting cosmic dance. This means that, at the quantum level, absolute nothingness may never have truly existed. Even the state that we define as nothingness, the vacuum of empty space, may contain a baseline level of energy and constant ephemeral fluctuations. In this context, the term unrealized potential may be a more accurate description of this state than the word nothingness. From a philosophical perspective, the concept of absolute nothingness also creates a deep logical paradox. How can nothingness, a state of complete non-being, give rise to existence? If something can come into being from nothing, then that nothing must have contained the potential for that something to exist. And if it contained potential, then that nothingness was not really nothingness at all. True, absolute nothingness must be a state in which there is nothing, including the very potential for existence. And such a state, by its very definition, should not be able to produce anything that exists. This logical circle suggests that the idea of something arising from absolute nothingness may be a conceptual impossibility. Ultimately, whether we look at it from a scientific or a philosophical perspective, the concept of nothingness is not as simple and as absolute as we might think. The nothingness that may have existed before the Big Bang was perhaps a much more complex, more energetic, and more creative scene than we can currently imagine. A sea of pure potential waiting for the right conditions to blossom into a universe. Although the Big Bang is generally defined in popular culture, and even in many scientific texts, as the absolute beginning of the universe, this definition is actually quite controversial on both scientific and philosophical levels. The word beginning implies a creation ex nihilo, a birth from a state of absolute nothingness. However, according to some of the most advanced and compelling theories in modern cosmology, the Big Bang may have been much more than a simple beginning. It may have been a moment of profound transformation, a transition from a previously existing cosmic order, another form of existence, or even another, older universe. From this perspective, the Big Bang may not have been a birth, but rather a cosmic restructuring, a violent and beautiful metamorphosis. Cyclical universe models, which are gaining increasing attention among theoretical physicists, align perfectly with this idea. According to these models, the universe is a phoenix-like structure that expands, then collapses, and is then reborn in a new fire. This cosmic cycle could last for trillions of years, and each collapse, or big crunch, could trigger the next Big Bang. If this is the case, then the Big Bang that we experienced 13.8 billion years ago was simply a moment of transformation that followed the death of a previous parent universe. This profound idea implies that the past of our universe could be infinite, a concept that fundamentally challenges our ingrained notion of a singular beginning. These ideas also find a deep resonance in the strange and beautiful world of quantum cosmology. In theories of the universe that begin with a quantum fluctuation, there may have been a state of pure quantum potential, something akin to an energy field, that existed before the Big Bang. This potential then, through some as yet unknown mechanism, transformed itself over time to create our universe. This perspective suggests that the universe formed naturally, as an inevitable consequence of the underlying laws of quantum physics, under a certain set of conditions. In this view, the Big Bang becomes a kind of evolutionary leap, not a true beginning from nothing, but an inevitable and natural transition point in the life of the cosmos. Ultimately, the question of whether the Big Bang was a beginning or a transformation is a key that could unlock our deepest understanding of the nature of the universe. If it was a singular beginning, then there is no before to speak of. But if it was a moment of transformation, then there may be a much larger, older, and more complex cosmic structure that lies behind our own universe. A structure whose history may stretch back into an infinite past. As science strives to resolve this profound distinction, we must also seek to make sense of this great unknown by looking at the problem through both the precise lens of physics and the broader, more contemplative lens of philosophy. Modern physics, and particularly Albert Einstein's revolutionary theory of general relativity, states that time is not an independent and absolute entity, but that it exists alongside space, woven together into a single, dynamic fabric. The fabric of space-time, as we now call it, is thought to have emerged and taken shape at the very moment of the Big Bang. Therefore, what we call time may have been born with the universe itself. If this is true, then time was a product of the Big Bang, and there was no dimension of time before it. This leaves us with a rather unusual and mind-bending question: if there is no time, what does the word before even mean? We humans are accustomed to thinking of everything as having a before and an after. But when we reach the very beginning of the universe, this habit of mind may lose its validity. If time itself begins at that point, then there can be no before in any meaningful sense. This is not just a logical dilemma, It is a concept that is deeply and profoundly challenging for our minds to grasp. However, some of the most advanced theories in physics, such as quantum gravity and string theory, suggest that our classical understanding of time as a smooth, continuous, and one-dimensional structure may be an illusion. These theories suggest that time, at the most fundamental, quantum level, may be discrete, made of tiny, indivisible units, or may even be a directionless and emergent property of a deeper reality. In these theories, time is not a universal, fundamental dimension, but a property that emerges from the relationships and interactions between events. In other words, time as we know it may not be what we think it is, but may be a more abstract and complex structure. In this case, there may have been a kind of proto-time, a different kind of temporal order, that existed before the Big Bang. Ultimately, the question of whether time began with the Big Bang remains one of the great unresolved issues in modern science. However, the physical models that we currently have strongly suggest that time, as we experience it, does have a beginning. This beginning represents not only a physical limit of our universe, but also a conceptual limit of our own understanding. Perhaps time is not simply a product of the universe, but is deeply ingrained in its very nature. And to fully understand the nature of time, we will need to understand the universe itself on a much deeper and more profound level. Science, by its very nature, is a discipline that relies on observation, on measurement, and on the empirical testing of our hypotheses. Therefore, it is incredibly difficult, if not impossible, to provide direct observational data about what happened before the Big Bang, a time and a place from which no light or information can ever reach us. However, this does not mean that scientists cannot say anything meaningful about that primordial period. Thanks to the power of our physical theories and the elegance of our mathematical models, a number of different and often competing hypotheses have been developed about what may have existed before the Big Bang. Among these, some of the most well-known and compelling are the models of a cyclic universe, the concept of brain cosmology, the idea of a universe born from a quantum fluctuation, and the theory of an eternally inflating multiverse of cosmic bubbles. For example, according to the cyclic universe model, our universe is not a one-time event, but is part of an endless cycle of expansion and contraction. In this view, the universe expands, then collapses back on itself in a big crunch, which then triggers the next Big Bang, giving birth to a new universe. Each of these cosmic cycles could be seen as the end of a previous universe and the beginning of a new one. In this case, the before of our Big Bang was simply the final, contracting phase of a parent universe. Another, and more exotic, approach is that of brain cosmology, which is inspired by string theory. This theory suggests that our entire three-dimensional universe exists on a giant, multi-dimensional membrane, or brain, and that it was born through the violent collision of our brain with another, parallel brain existing in a higher dimensional space. In this model, the Big Bang is the result of an interaction that occurred in another, higher dimension. Quantum cosmology, on the other hand, offers a more radical and perhaps more fundamental proposal. According to this theory, our universe originated from a vacuum fluctuation at the quantum level. In other words, the entire universe, with all its matter and energy, could have come into existence as a sudden and spontaneous burst of energy in the quantum vacuum, a state of pure potential. In this model, there is no classical before, because time and space themselves would have emerged at the moment of this quantum event. Thus, science is now seriously considering the idea of a timeless and spaceless origin for our universe. While science does not yet have a definitive and proven answer on this profound matter, every new theory that it presents shows us that the beginning of the Big Bang is far more complex, more strange, and more beautiful than we had previously imagined. It may be a mystery that we can never fully and completely understand. However, Science does not, and will not, cease to ask these fundamental questions, and with each new question it asks, and each new theory it proposes, it expands the boundaries of our knowledge a little further into the great unknown. Could our universe have been born from another, older universe? This remarkable and mind-bending idea is one of the hypotheses that is gaining increasing attention and credibility in the world of modern cosmology. The theory of the multiverse, in its various forms, argues that our universe is not all that exists, but that it is only one of many, and that other parallel universes may exist alongside our own. If this is true, then it is entirely possible that our universe could have been born from another universe, perhaps from its collapse, or from a quantum fluctuation within its fabric. In this view, our universe would become just one small part of a much larger and more ancient cosmic web. Some theories, particularly those related to the concept of brain cosmology, suggest that our universe was formed by the violent collision of our own brain universe with another parallel brain universe. This cataclysmic collision could have caused a massive and instantaneous release of energy, which would have then led to the hot, dense state of the Big Bang. If this model is correct, then the birth of our universe is actually the result of an interaction that occurred on a much broader, higher dimensional plane. In other words, our universe could be seen as a kind of cosmic child, born from the meeting of two parent universes. Another, and perhaps even more popular, model is the bubble universe theory, which arises from the theory of eternal inflation. According to this theory, new universes are continuously forming, like bubbles in a pot of boiling water, in a background of eternally expanding quantum space. In this scenario, some of these bubbles expand and cool on their own to become full-fledged universes. Like our own, our universe would be just one of these many bubbles. If this is the case, then the birth of our universe could be seen as an entirely random, but physically possible, event. However, there are likely to be fundamental physical laws that govern this process of cosmic randomness, and these laws may operate differently in other different universes. Ultimately, the possibility that our universe was born from another universe offers us a new and radical perspective on the question of our cosmic origins. This idea allows us to see our universe not as a singular, isolated creation, but as a small and perhaps insignificant part of a much larger, and possibly infinite, whole. In this vast and complex cosmic system, universes are born, they expand, they collapse, and they may be replaced by new ones in an endless cycle of creation and destruction. Perhaps our universe is just one single, fleeting link in this endless and beautiful chain of cosmic creation. One of the most intriguing and mind-bending hypotheses about the origin of our universe is the idea that it may have originated from within, or under the direct influence of, another pre-existing universe. This idea is explored in a number of different theoretical frameworks, particularly those of the multiverse and brain cosmology. If our universe was indeed born from within another, or from a collision with another, this would require us to completely reconsider our understanding of the nature of universes, seeing them not as isolated and independent entities, but as interactive and continuous processes. The other universe that is mentioned in these theories is not merely a place that is physically different from our own. It could be a reality that is entirely and fundamentally distinct in terms of its natural laws, its flow of time, and even its fundamental dimensional structures. In other words, our universe could have emerged as the result of a system that is vastly and perhaps incomprehensibly different from our own. The theories that are known as brain cosmology, or membrane cosmology, have proposed that our entire universe exists on a giant three-dimensional membrane, or brain, that is floating within a much larger, higher dimensional space, often called the bulk. In this picture, the event that we call the Big Bang could have occurred as a result of the violent collision of our brain with another parallel brain. Here, the other universe refers to another brain structure that exists in another dimensional plane, but is capable of interacting with our own. The collision of these two immense membranes could have released a tremendous amount of energy into our universe, much like the friction that is generated between two rocks when they are struck together can produce sparks. This released energy would have then given rise to the matter, the time, and the space of our own universe. This radical idea suggests that the Big Bang was not a singular beginning, but was merely a local event that occurred within a much larger and more ancient system. However, some cosmic clues may bear the faint and subtle traces of such a dramatic scenario. For example, certain large-scale anomalies that have been observed in the cosmic microwave background radiation, such as the so-called cold spot, have led some scientists to consider the possibility that this event may not have been a universal birth, but rather the byproduct of a larger, external event, such as a collision with another bubble universe. Although such observational findings have not yet been clarified and are still highly debated. If we did indeed originate from another universe, this would indicate that our existence is just one small part of a much larger and more complex system. This also implies that our universe came into existence not only through its own internal dynamics, but also through an external interaction. This idea is philosophically striking because it approaches the concept of creation not through a single, absolute first cause, but through a process of continuity and interconnectedness. If every universe is born from another universe, where does this cosmic chain end? Is there an infinite and eternal loop of creation? Or is there a first, triggering universe that started it all? These are the kinds of questions that require us to think deeply, not only about the nature of physics, but also about the most profound philosophical dimensions of our own existence. Perhaps universes, like living organisms, are born, they develop, and they eventually give way to new and different formations in an endless cosmic cycle. When considered within the framework of the strange and probabilistic world of quantum mechanics, the very emergence of our universe could be seen as the product of a single, random event. This idea may seem frightening or even absurd at first glance, as we typically assume that a system as orderly, as vast, and as complex as the universe must have emerged through some conscious, or at least some guiding and deterministic mechanisms. However, in the quantum world, reality operates in ways that do not easily align with our classical, everyday logic. It has been proposed that the universe could have emerged from a state of nothingness known as the quantum vacuum, a state where there is no matter, no time, and no space. Yet it still contains a vast reservoir of potential energy, as a result of a single, random quantum fluctuation. This potential could have been realized. This accidental creation hypothesis was first proposed by the renowned physicist Edward Tryon in the 1970s. Tryon famously asked, "Why shouldn't the universe be a quantum fluctuation?" This perspective views the origin of the universe as an unexpected, yet physically possible, outcome of the inherent energy fluctuations that exist in a quantum vacuum. In other words, the universe could have accidentally come into existence as a system with a net energy of zero, provided that its positive and negative energy components remain in perfect balance. In such a model, no external cause is required for the universe's emergence. Probability alone is sufficient. However, the emergence of a highly ordered and structured universe from this initial, accidental formation remains an unresolved and deeply perplexing question. The fact that our universe not only exists, but is also exquisitely and finely tuned to allow for the existence of life, raises the profound question of whether this initial randomness was somehow limited or directed. For this reason, the idea of an accidental formation is often considered alongside other concepts, such as the anthropic principle, perhaps among billions of other failed universes that may have also fluctuated into existence. The only one that has the right order and the right laws to allow for the emergence of life is our own. In this view, we are here simply because we can be here. If the universe were any different, there would be no one to observe it. Therefore, the idea that the universe arose by chance becomes not only a physical question, but also a deeply existential one. If everything is the result of a cosmic roll of the dice, How does this affect our place in the universe and our search for meaning? Is the emergence of conscious beings in a universe that came into being by chance a true miracle? Or is it simply a part of the universe's grand and impersonal game of probabilities? Such questions demonstrate that our scientific models of the nature of the universe must go hand in hand with deep and careful philosophical thought. Time is one of the most fundamental and essential building blocks of our perception of reality. Everything we experience, everything we remember, everything we plan for, flows and is organized based on the relentless and seemingly one-way arrow of time. Our memories remain in the fixed and unchangeable past, and our plans are directed toward an open and uncertain future. However, the question of whether time is an objective and fundamental feature of the physical realm, or is merely a product of our perception, a kind of grand illusion, is still a matter of intense and ongoing debate. In some of the most advanced and speculative theories in physics, time is considered not to be a fundamental property of the universe itself, but rather a context that is defined by the observer in relation to the events they witness. In this case, time may not actually exist as a fundamental entity, and our experience of its passage may be merely a result of our own consciousness and our interaction with the universe. In particular, studies in the field of quantum gravity have suggested that time is not a universal, absolute dimension, but is a process that can vary and even break down depending on the events and the scales at which they are observed. Some models, such as string theory, argue that time is not something fundamental, but is merely a derivative property that emerges from deeper and more complex physical processes. If this is true, then a reality that exists outside of time is not just possible, but may be the fundamental state of the cosmos, and the origin of our universe may have occurred from this non-temporal plane. This perspective suggests that the very concepts of before and after, which we use to describe the origin of the universe, may be deeply and fundamentally misleading. Additionally, some cosmological scenarios have been proposed that assume the universe had a timeless beginning. For example, the famous no-boundary proposal, developed by Stephen Hawking and James Hartle, suggests a quantum mechanical model in which the universe has no definitive starting point, and in which time is curved and finite, much like the surface of a sphere. According to this model, the past of the universe is not a singular point, but a smooth, rounded surface. In this case, time as we know it may not have existed in the classical sense at the very beginning of the universe, and it may have only emerged as a distinct and linear dimension as the universe began to expand and cool. The possibility of a reality that exists outside of time is a concept that is quite difficult for the human mind to comprehend, as we are hardwired to conceptualize everything in terms of a linear and forward-moving timeline. However, the laws of physics themselves suggest that the universe does not have to operate in this familiar way. If there is indeed a reality outside of time, then perhaps the true origin of the universe lies in this timeless plane. This could completely and fundamentally redefine our concept of a beginning. Perhaps, to truly understand the birth of our universe, we need to start thinking beyond the confines of time itself. If time did indeed begin with the universe, then there must have been some element or some event that triggered its beginning. However, this very idea contains its own deep and perplexing paradoxes. How can a thing exist before time begins? For that thing to exist and to have an effect, it would seem to require a temporal framework in which to act. For this reason, many scientists do not rely on the classical linear relationship of cause and effect to explain the beginning of time, but rather on a more fundamental physical or quantum transitional process. Perhaps what initiated time was not a cause in the sense that we normally understand it, but was rather the spontaneous realization of a natural, inherent potential. Quantum cosmology models provide a strong and compelling foundation for this very idea. For example, the concept of the universal wave function, a central idea in quantum cosmology, argues that the entire universe transitioned from a timeless, probabilistic quantum state to a classical, deterministic universe. This transition can be thought of as a kind of cosmic scale wave function collapse. In this view, time may have emerged as a direct result of this collapse. In this case, the ultimate initiator of time could have been a purely quantum event, one that occurred spontaneously and without a prior cause when a certain energy level was reached. It does not require any conscious or external cause, but is based solely on the principles of physical necessity and quantum probability. According to another, related hypothesis, time may have emerged as a direct consequence of the expansion of the universe. In other words, as space began to expand, time began to flow. This model suggests that time is not a fundamental driver of cosmic events, but is a byproduct of the dynamic and evolving behavior of the universe. In this sense, time is not the motor of the universe, but is an emergent property of its motion. Without the expansion of the universe, time itself would not exist. This leads us to view the beginning of time not as a singular cause, but as a fundamental condition of our universe's existence. While all of these theories are attempting to explain the beginning of time from different perspectives, they all share a common and profound thread: time may have emerged suddenly. But this emergence is not a process that can be easily explained by our familiar, classical cause and effect relationships. To truly understand the origin of time, we may need to approach its very nature in a completely different and more fundamental way. Perhaps time is as fundamental to our very understanding of the universe as it is to the universe's own emergence. We usually think of time as an abstract and unchanging framework, a kind of invisible grid on which the events of the universe play out. But modern physics, and in particular Albert Einstein's theory of general relativity, has deeply and profoundly questioned this classical concept. General relativity has shown us that time is not absolute, but is a dynamic and malleable quantity that can be bent and warped by the presence of mass and energy. This demonstrates that time is not merely a passive flow, but is an active and interactive dimension of the material universe. Even if time itself is not a form of energy, if it is so directly and intimately related to energy, then it is possible that time emerged, or was produced, alongside the emergence of matter and energy at the beginning of the universe. This idea strongly supports the possibility that time, like everything else, could have had a definitive beginning. When we consider the very origin of the universe, studies in the field of quantum gravity suggest that time might be a derivative property of the fundamental energy fields that existed at the beginning of the universe. In the very first moments, below the so-called Planck time, which is approximately 10 to the power of minus 43 seconds, time and space could not be defined in the classical sense. At this incredible scale, energy is so dense and so concentrated that the very fabric of space-time is thought to merge with the chaotic and roiling sea of quantum fluctuations. This means that time had not yet emerged in its familiar, classical sense, but may have had a quality that evolved and changed alongside the evolution of energy itself. Perhaps time became organized and gained its familiar, linear flow only as the universe began to expand and cool, and as the primordial energy began to distribute itself into more stable and structured forms. If time is indeed a phenomenon that is deeply and fundamentally connected to energy, this holds significant and profound clues not only about the beginning of our universe, but also about its ultimate future. It is possible that time itself may change as the energy structure of the universe dissolves, as entropy increases and the universe approaches its final state of heat death. The very flow of time may slow down, or even stop, or perhaps change its direction. In this context, it can be thought that the direction of the arrow of time is determined not only by the sequence of physical events, but also by the general course of the distribution of energy in the entire universe. Such an approach suggests that time is not merely the passive sequencing of events that occur within the universe, but is also a direct and active result of the universe's own energetic structure. Philosophically, this view makes the question of what existed before time much more meaningful. If time is also a phenomenon that emerged later, just like matter and energy, then the question, what was there before time began, can be transformed into a more physical and perhaps more answerable question. What was the nature of energy before it gave rise to time? This subtle but important shift in perspective moves us away from purely metaphysical and abstract thinking and brings the question of the beginning of the universe into a more measurable and experimentally investigable realm. When we consider that the universe is not merely a collection of matter, energy, and space-time, but that it also contains a vast and ever-increasing amount of information, we arrive at a more complex and multi-layered reality. Information, in this context, is the sum of all the order, the structures, the physical laws, and the possibilities that exist in the universe. From the perspective of quantum physics, every single particle in the universe carries information through its wave function, which describes its state and its probabilities. Therefore, the moment of the universe's birth may not have been only a physical beginning, but also the birth of information itself. In a very real sense, the entire universe can be perceived as a vast and complex data set. The positions, the speeds, the interactions, and the probabilities of all the particles that make up the cosmos, all of these elements, may have been encoded in the very first moment of the universe's existence. This profound idea is particularly explored within the framework of the holographic principle. According to this speculative but powerful principle, all of the information that is contained within a volume of the universe may be completely encoded on the boundaries of that volume, on a more fundamental two-dimensional plane. If this information did indeed emerge at the very beginning of the universe, then the Big Bang could have been not just a release of immense energy, but also a kind of cosmic decoding process. It is analogous to a computer loading its operating system after its basic input-output system, or BIOS, has been initiated. In this view, the universe might have started with a fundamental matrix of information, a kind of cosmic code that contained all the necessary laws, constants, and probabilities that would determine how the universe would operate and evolve over time. We can also reach some interesting conclusions about the role of information through the concept of entropy. As entropy increases, the overall order of a system decreases, but the information it contains is not lost. It simply becomes more disordered and harder to access. Therefore, the existence of a very low entropy, highly ordered state at the beginning of the universe indicates that it must have contained a very high level of structured information. With the expansion and evolution of the universe, it is thought that this initial information has been dispersed and transformed into the vast and complex structures that we see today: the galaxies, the stars, the planets, the DNA of living organisms, and even consciousness itself. All of these are the complex and beautiful evolutionary results of that initial, compact core of cosmic information. From a philosophical perspective, this view forces us to re-examine the very meaning of the universe and its relationship with consciousness. If information is an inherent and fundamental property of the universe, this could indicate that the universe is not a random or chaotic system, but has a deeply information-oriented structure. Perhaps the universe is evolving in a way that is designed to produce and process information, and to eventually observe itself through the emergence of consciousness. This idea opens the door to the concept of a cosmic purpose. Information could be the universe's way of communicating with itself, of becoming aware of its own existence. In this grand and beautiful picture, the Big Bang was not just a beginning, but also a kind of end. The Big Bang is traditionally and widely accepted as the moment of the universe's birth, the beginning of all things. However, some of the most advanced and compelling theories in modern physics suggest that this cataclysmic event may not have been just a beginning, but may also have been the end of a previous, older universe. This profound view is particularly common in the cyclical universe models that we have explored. In this picture, universes are born, they expand, they collapse, and then they are reborn in an endless cycle. The Big Bang may have been the first brilliant spark of a new cosmic cycle that followed the Great Collapse, or the Big Crunch, of a previous parent universe. This suggests that the universe is not a one-time, singular formation, but is a constantly renewing and evolving system. One specific type of these cyclical models is the Big Bounce model. According to this model, at the point where a previous universe collapsed due to its own immense density, time and space were, in a sense, reset, and then a new expansion began through the powerful effects of quantum gravity. Our universe, in this case, would be the result of this cosmic bounce. The Big Bang is therefore both a moment of birth and a moment of death. It is thought that some of the information, the energy, or even the fundamental structures from the previous universe could have been transferred to our own universe through this bounce. In this view, our universe is not entirely new. It may be the heir to a previous, long-lost existence. If the Big Bang is indeed the beginning of an end, this idea also fundamentally redefines our understanding of the nature of time. Time may not be a linear and one-way street, but may be cyclical, like a great cosmic wheel. Each universe begins and ends its own particular chapter of time, but the overall process of time itself may be eternal. In this case, the very concept of an absolute beginning and an absolute end becomes meaningless. Everything in the cosmos exhibits a profound continuity through a constant process of change and transformation. This also provides us with a deeper and perhaps more comforting insight into the meaning of existence itself. In this picture, death is not an absolute annihilation. It is merely the gateway to a new and different birth. This view is a powerful one, both scientifically and philosophically. The profound symmetries that are observed in our universe, the conservation of its physical constants, and the relentless and mysterious arrow of time may all bear the faint and subtle traces of a cyclical and eternal system. In such a system, the future of our universe may be to inevitably return to its own beginning. Perhaps the universe that we are currently experiencing is just the last, fading cry of the past, and at the same time, the very first, brilliant breath of the future. Whether time has a definitive beginning is one of the most fundamental and deeply debated questions in all of modern science. If time did indeed begin suddenly, at an absolute and singular 0 point, then everything that existed before that point would be undefined, or perhaps non-existent. However, is this 0 point truly absolute? Or is it merely a relative reference point in a much larger and more complex cosmic story? The event that we call the Big Bang, which is widely accepted as the beginning of our universe, was not actually an explosion in the classical sense. It was the moment when space-time itself began to expand. Therefore, when we speak of the beginning of time, we may actually be referring to a moment of transition rather than a singular physical event. In modern cosmology, the Planck time is generally accepted as the effective 0 point of time, as far as our current physics can describe. This is an incredibly and almost unimaginably short duration. Approximately 10 to the minus 43 seconds after the Big Bang, we have no definitive information about what may have come before this point. This is because the current laws of physics, including Einstein's general theory of relativity, lose their validity at this extreme scale. However, at this point, the very term beginning may be more of a reflection of the boundary of our current knowledge than a statement about the true nature of reality. Perhaps time gained its familiar, continuous flow by crossing this quantum threshold. In other words, time did not suddenly emerge from nothing. It may have gradually taken shape from a more fundamental, timeless state. This suggests that the emergence of time was not a birth, but a formation. Some of the most advanced theories in physics propose that time may have already existed in a different and unfamiliar form at this so-called 0 point. According to these theories, time may have existed in a different dimension or as a different kind of structure before the birth of our universe. With the expansion of the universe, It began to flow in the linear way that we are familiar with, and we are now witnessing it in this particular form. In this case, the 0 point is merely a moment of rupture in our own perception of time. In reality, time itself may have been a much more complex and multifaceted entity. This debate is not only a scientific one, but also a deeply metaphysical one. The idea of an absolute 0 point for time implies that the universe was created, and that this creation was a singular event that was limited to a single moment. However, the idea that time is a process suggests that the universe came into existence through a more natural and gradual development. This, in turn, leads us to rethink our most fundamental concepts, such as creation, cause, and purpose. The fundamental question of whether time is an absolute and fundamental feature of the universe, or an emergent and relative one, continues to drive the frontiers of both physics and philosophy. Symmetry breaking is a critical and profound concept in modern physics, and it is especially important in the field of cosmology. It is thought that in the very first, incredibly hot and dense moments of the universe, all of the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces may have behaved as a single, unified superforce. This primordial period was characterized by extremely high temperatures and energy levels, a state of perfect and beautiful symmetry. However, as the universe began to expand and cool, these unified forces began to separate and to differentiate from one another. This process is what physicists call symmetry breaking. In other words, while the universe initially possessed a state of perfect and profound symmetry, this symmetry gradually and inevitably broke down, giving rise to the rich and complex diversity of forces and particles that we observe in the universe today. The process of symmetry breaking does not merely signify the separation of the fundamental physical forces, it also led to the crucial imbalance between matter and antimatter, the emergence of mass itself, and the formation of the fundamental structural foundation of the entire universe. For example, it is thought that particles gain their mass through their interaction with the Higgs field, a process that is itself a result of a specific kind of symmetry breaking. If this symmetry had not been broken, then all particles would be massless, and neither atoms, nor galaxies, nor stars, nor life itself could have ever formed in the universe. Therefore, all of the incredible diversity and complexity that we observe in the structure of the universe today is the direct result of a series of microscopic imbalances and symmetry-breaking events that occurred in those first, fleeting moments of cosmic time. How these breaks in symmetry occurred at the quantum level is still not fully understood. However, our mathematical models suggest that these breaks were not chaotic or random, but that they occurred within a specific and well-defined set of rules, and were governed by a highly delicate distribution of energy. In other words, the asymmetrical and complex structure of our universe is actually a broken form of a much deeper and more delicate underlying symmetry. What is so intriguing is that this process of breaking was not random, but was the product of a specific and inherent physical logic. This shows us that the universe has a fundamental structure that simultaneously contains both a deep and profound order and an incredible potential for diversity. The concept of symmetry breaking also has deep and resonant philosophical implications. The universe that emerges from the breaking of a perfect and pristine symmetry is similar to a work of art that gains its unique beauty through a deliberate and well-placed flaw. According to this idea, it was the universe's very deviation from a state of sterile perfection that brought with it the fundamental characteristics that make our cosmos a habitable and life-bearing place. Perhaps existence itself, in all its messy and beautiful complexity, is only possible through the conscious or unconscious breaking of a perfect and underlying symmetry. The laws of physics, as we understand them, determine the fundamental rules of all the events that we observe in the universe. However, the question of when and how these elegant and powerful laws came into existence remains one of the great and enduring mysteries of science. Many scientists believe that the laws of physics were established at the very moment of the Big Bang, or in the first few fractions of a second that followed. In other words, it was not only matter and energy that came into existence with the birth of the universe, but also the fundamental and immutable laws that would govern the behavior of these materials for all of time. This suggests that physical reality consists not only of content, but also of a set of inviolable rules. The Big Bang may have created not only the matter of the universe, but also the very rules of the cosmic game. However, this idea raises some very deep and difficult questions. Are the laws of physics independent of the universe, or did they emerge with the universe itself? In other words, do these laws exist in some abstract, timeless, Platonic realm, above and beyond the universe, or are they an integral and emergent part of it? If they are independent of the universe, this seems to place them in a metaphysical realm that is beyond the reach of science. If they are an integral part of the universe, then this opens up the possibility that they are not fixed and immutable, but are dynamic and could even be evolutionary. Some physicists have therefore suggested that the laws of physics themselves may have evolved over time. Perhaps these laws were different in the very early and extreme stages of the universe, and the rules that we observe today are the ones that stabilized over the course of cosmic time. Another intriguing and related question is why the laws of our universe seem to be so exquisitely and finely tuned to allow for the existence of life. Even a very small and seemingly insignificant change in the value of the fundamental physical constants could have made the formation of complex structures impossible. This delicate and seemingly improbable balance has led some scientists and philosophers to believe that the laws of physics did not arise randomly, but through some specific and underlying logic or necessity. Perhaps, as the multiverse theory suggests, there are many other universes where different physical laws apply, and the laws in our particular universe are observable by us only because they are the ones that allow for life to exist in the first place. This also implies that the Big Bang could have been a moment of cosmic selection, a process that determined which of the many possible sets of universal laws would allow for a stable and continuing reality. The relationship between the laws of physics and the beginning of the universe is a profound debate that brings science and philosophy into close and intimate contact. If these laws were indeed written at the very beginning of the universe, then we are talking about a kind of cosmic software. But who, or what, wrote this software? Or did the universe, in some strange and beautiful way, code itself? These are the kinds of questions that have both deep physical and profound ontological dimensions, and they continue to guide us in our quest to understand the fundamental nature of our universe. The Big Bang theory is often associated with the concept of a singularity. A singularity in this context is a point where time and space are thought to have been compressed into a zero volume, and where the density of matter and energy was infinite. However, this very concept represents a point where the current and well-tested laws of physics, including Einstein's general theory of relativity, no longer apply and cease to make sense. In other words, a singularity is actually an unknowable limit of our theories, a mathematical artifact that signals the breakdown of our physics, rather than a true description of physical reality. For this reason, some of the most prominent physicists in the world have begun to question whether a singularity actually existed at the beginning of the universe. Perhaps the beginning of the cosmos was not a point of infinite density, but rather a different and more complex structure, with distinct physical properties that may be defined by the laws of quantum gravity, a theory that we have yet to fully understand. According to some of these theories, the singularity is a consequence of our classical, and therefore incomplete, understanding of physics. However, in the framework of quantum gravity models, this problematic infinity may be replaced by a more stable and definable transition region. For example, the concept of a Planck foam or a quantum spacetime structure argues that spacetime itself is not a smooth and continuous fabric, but is discontinuous and foamy at the smallest possible scales. In this picture, These fundamental quantum structures would replace the classical singularity. In this case, before the Big Bang, there was not a void or a nothingness in the classical sense, but rather a realm of highly dense and energetic quantum fields. Alternatively, some theories have proposed that our universe sprang back into existence after the collapse of a previous parent universe. In this model, the singularity is not an end or a beginning, but a transition point, like a spring that compresses to a maximum and then expands again. In this view, the universe moves in an infinite number of cycles. This approach proposes a cosmology in which the singularity is negated, and the universe exists as a continuous and eternal entity. In such cyclical models, time is also continuous, which means that the concept of before the Big Bang once again gains a real and meaningful sense. Philosophically speaking, the very concept of a singularity takes us both to the absolute limits of our current scientific knowledge and beyond the very bounds of our human imagination. If the singularity is merely a hypothesis, a placeholder for our ignorance, then perhaps we need a very different, more intuitive, and more conceptual understanding of the true origin of our universe. The idea that something other than a singularity could have existed before the Big Bang is a profound challenge that is pushing the boundaries of modern science and is requiring us to develop larger, more comprehensive, and more beautiful models to understand the deep and mysterious nature of our universe. The idea that the entire universe works like a vast and complex information processing system is a concept that has been intensely and increasingly debated in both scientific and philosophical circles, especially in recent years. According to this radical and compelling approach, the universe does not merely contain energy and matter, it also produces, processes, and stores information, much like a giant cosmic computer. In this framework, the universe can be seen as having all the components of a computational system. It has input data, which are the initial conditions of the universe. It has processors, which are the fundamental laws of physics, and it has outputs, which are the complex structures that we see today, including consciousness and life itself. This idea is gaining increasing acceptance and support, particularly within the framework of quantum information theory and the holographic principle. In this view, information lies at the very core of the universe. Matter and energy may be just the physical manifestations of this more fundamental, informational reality. According to this approach, every single physical event that occurs in the universe is, at its heart, a process of information processing. For example, the collision of two elementary particles is not merely an exchange of energy and momentum, it is also a transfer and a transformation of information. In this view, information exists not only in the written or digital systems that we create, but is an inherent and fundamental property of nature itself, existing within the hearts of stars, in the elegant spirals of our DNA, and in the strange and beautiful world of the quantum fields. If this is true, then to understand the fundamental workings of our universe, we would require not only the tools of physics, but also the principles of information theory. The processing of information may be a fundamental property of the universe at both the smallest, microscopic scales and the largest, macroscopic levels. The holographic principle, a speculative but powerful idea from string theory, seems to reinforce this concept. According to this principle, all of the physical information that is contained within a three-dimensional region of space can be completely and perfectly stored on its two-dimensional boundary surface. This implies that the universe itself could operate like a giant and complex hologram. Every point in the universe may, in some way, carry information about the whole. In this case, we ourselves would be a form of data processor existing within this vast information system. The human mind, in this picture, may be a highly evolved and specialized information point, a way for the universe to recognize, to process, and to recode itself. This profound idea takes the relationship between consciousness and the universe to a whole new and exciting level. If the universe is indeed an information processing system, then could this system have a purpose or a direction? Perhaps the universe is constantly trying to establish a kind of balance by producing more and more complex information to counteract the relentless increase of entropy. Or perhaps the universe itself is not conscious, but it operates in such a way as to make room for the emergence of structures, like living beings, that can continue the process of information processing. These are the kinds of thoughts that are deepening both our scientific and our metaphysical inquiries. Perhaps the universe exists for the sole purpose of reaching a state where it can produce information processors that are advanced enough to understand it. The concept of nothingness is perhaps one of the most challenging and perplexing ideas for the human mind to grasp. This is because we are so accustomed to thinking about things, to imagining entities, or to contemplating states of being. However, the concept of nothingness represents a state in which there is no time, no space, and no existence of any kind. Can such an absolute nothingness really exist? Or is it merely a mental abstraction, a concept that has no counterpart in reality? The answer to this profound question is of great importance at both the philosophical and the physical levels. Because if a state of absolute nothingness did indeed exist before the Big Bang, then the very emergence of something from this nothingness would shake the very foundations of all the cause and effect relationships that we know and understand. Physically speaking, even an absolute vacuum is not actually a state of true nothingness. According to the principles of quantum field theory, the state that we call the vacuum of empty space is actually filled with a seething sea of energy and is constantly creating pairs of virtual particles and antiparticles. This shows us that a state of true, absolute nothingness, a state with zero energy and zero activity, cannot be observed in nature. There is no region of the universe that is at absolute zero temperature, or is completely and utterly devoid of energy and motion. If a state of absolute nothingness is truly impossible, then there must have been something that existed before the Big Bang. Perhaps this something had a structure that was very different from our classical physical intuition. Philosophically, the concept of nothingness is also deeply controversial and paradoxical. The very question, if there is nothing, who or what is observing it, brings up the deep and intimate relationship that exists between existence and consciousness. Perhaps the very concept of nothingness can only be defined by the existence of something. In this view, nothingness only gains its meaning in contrast to the concept of existence. In this case, the idea that a state of true and absolute nothingness cannot exist becomes even stronger. Perhaps existence is nothingness denying itself. Such thoughts open the door to deep and intuitive questions about the fundamental nature of our universe. Scientists have developed a number of different and often competing theories to try to answer the profound question of how something can come from nothing. According to some of these theories, quantum fluctuations in a primordial vacuum made it possible for our universe to emerge. However, the important and subtle point here is that even this quantum vacuum is not actually a state of true nothingness, because the laws of physics and the quantum fields themselves are still thought to be present in this state. Therefore, even the vacuum state that is often presented as the ultimate starting point of the universe contains a deep and underlying order and a vast potential for existence. This shows us that the concept of absolute nothingness may be nothing more than a useful, but ultimately misleading, concept.
In the vast darkness of space, a single galaxy burns bright enough to rewrite everything we thought we knew about cosmic history. This galaxy existed when our universe was barely 290 million years old, just 2% of its current age. But this ancient light carries secrets that challenge our deepest theories about how galaxies form, how quickly stars can ignite, and whether the universe itself might be hiding inside something unimaginably vast. From impossible brightness to missing black holes, From chemical fingerprints that should not exist to theories that place our entire reality within a cosmic prison. Prepare yourselves. Deep in the constellation Fornax, astronomers discovered something that should not exist. A galaxy that burns with the light of hundreds of millions of suns. Yet it formed when the universe was barely out of its infancy. Named Jade's GS Z14-0. This cosmic lighthouse shattered every distance record we had ever set. At a redshift of 1432, it dates back to less than 300 million years after the Big Bang, pushing our view deeper into time than ever before. To understand how extraordinary this discovery truly is, picture the universe as a 13-year-old child. This galaxy would have existed when that child was barely 3 months old. The light we see today began its journey across 13.5 billion years of expanding space. Stretched and reddened by the universe's own growth, the James Webb Space Telescope observed this galaxy for almost 10 hours using its near-infrared spectrograph. And when scientists first processed the spectrum, they knew they were looking at something unprecedented. The previous record holder, another galaxy discovered just years earlier, suddenly seemed almost modern in comparison. But distance alone was not what made this discovery so startling. Jade's GS Z14-0 is over 1,600 light-years across, proving that the light we see is coming mostly from young stars and not from emission near a growing supermassive black hole. For a galaxy this early in cosmic history, such a size defies our expectations. Imagine trying to build a massive city in just the first few days after breaking ground on an empty plot of land. That is essentially what this galaxy accomplished in cosmic terms. The building blocks of matter had barely had time to cool and clump together when this galaxy was already blazing across the early universe. The source was surprisingly bright, which we wouldn't expect for such a distant galaxy. Astronomers admitted, in the infant universe, galaxies should be small, faint, and struggling to form their first stars. Instead, this ancient giant glows with an intensity that rivals much younger, more mature galaxies we observe in our cosmic neighborhood. The discovery forced scientists to question fundamental assumptions about galaxy formation. How could something so massive and luminous exist so early? What processes could have assembled so much matter and ignited so many stars in such a remarkably short time? Its age, size, and luminosity added to a growing body of evidence that current theories of early star and galaxy formation are incomplete. This single point of light in the darkness was telling us that the early universe was far more active and dynamic than our models had predicted. When astronomers split the light from Jade's GS Z14-0 into its component wavelengths, they uncovered a chemical signature that challenged everything we knew about the early universe. The galaxy was rich in nitrogen, unusually rich for such an ancient object. This discovery was like finding a sophisticated wine cellar in a house that was supposedly built yesterday. Nitrogen is not a primordial element that existed at the universe's birth. Instead, it must be forged inside stars and scattered into space when those stars die. Jade's analysis indicates that the brightness of the source, implied by the mere observation, is above what would be extrapolated from the measurements by the other Webb instruments, indicating the presence of strong ionized gas emission in the galaxy in the form of bright emission lines from hydrogen and oxygen. But nitrogen presented an even deeper puzzle. In the cosmic timeline, hydrogen and helium were the only elements present after the Big Bang. Every other element, from carbon to iron to nitrogen, had to be manufactured inside stellar furnaces over millions or billions of years. Stars live, burn through their nuclear fuel, and die, scattering these newly created elements into space, where they can be incorporated into the next generation of stars. This process takes time, Lots of time. For a galaxy to be nitrogen-rich just 290 million years after the Big Bang, multiple generations of massive stars would have had to live entire life cycles, die in spectacular explosions, and seed the surrounding space with their chemical products. Imagine trying to find evidence of a great-grandparent's recipes in a cookbook written on the day a family first settled in a new country. The presence of complex, refined ingredients would suggest that many generations had already passed, even if the official records claimed otherwise. This chemical fingerprint matches what we see in some of the oldest star clusters orbiting the Milky Way, suggesting that Jade's GS Z14-0 is forming stars in extremely dense environments. The connection between this ancient galaxy and the oldest stellar populations in our own cosmic neighborhood implied that rapid, intense star formation was occurring under conditions we had not fully understood. The nitrogen abundance pointed to what astronomers call chemical evolution happening at an accelerated pace. Normally, this process unfolds over billions of years as successive generations of stars gradually enrich their surroundings with heavier elements. But Jade's GS Z14-0 appeared to have compressed this timeline dramatically. That means galaxy evolution may have started much earlier than we thought. If massive stars were forming, living, and dying fast enough to produce significant nitrogen enrichment within the first few 100 million years of cosmic history, then the universe was far more active in its youth than our models predicted. The chemical fingerprints suggested that this galaxy was not a pristine, first-generation object, but rather the product of an already complex stellar ecosystem. Jade's GS Z14-0 was supposed to be an impossible outlier, a cosmic fluke that defied all expectations about the early universe. Instead, it opened the door to a much larger mystery. Given the relatively small region of the sky that we searched to find Jade's GS Z14-0, its discovery has profound implications for the predicted number of bright galaxies we see in the early universe. If such luminous objects could be found in a tiny patch of sky, how many more were waiting to be discovered across the vast cosmic landscape? Think of it like finding a bustling city while exploring what you thought was an empty wilderness. The discovery would immediately raise questions about how many other cities might exist in unexplored regions. Astronomers faced a similar situation as they realized that bright early galaxies might be far more common than anyone had imagined. Since its science observations began in July 2022, the JWST has discovered a series of increasingly distant ancient galaxies. Each new discovery pushed the boundaries further back in time, but also revealed that the early universe was populated with objects that should not have existed yet. The James Webb Space Telescope had only surveyed a minute fraction of the entire sky, yet it was consistently finding these bright, ancient galaxies. Statistical analysis suggested that there could be hundreds or even thousands of similar objects scattered across the cosmic deep field, each one representing a challenge to our understanding of early galaxy formation. Astronomers have used data from NASA's James Webb Space Telescope early release observations and discovered 87 galaxies that could be the earliest known galaxies in the universe. This growing population of ancient, bright objects was rewriting the cosmic census. Previous models had predicted that early galaxies would be small, faint, and rare. The universe should have been a relatively quiet place in its first few 100 million years, with star formation proceeding slowly and inefficiently. Instead, astronomers were finding evidence of vigorous stellar nurseries operating at full capacity when the cosmos was still in its infancy. These ancient, bright galaxies, sometimes called little red dots, are popping up across JWST's surveys. The nickname little red dots came from their appearance in early telescope images. But these objects were proving to be anything but insignificant. Each new discovery added weight to the growing realization that the early universe was far more active and structured than theoretical predictions had suggested. If bright galaxies were common in the cosmic dawn, it meant that the processes of star formation, element creation, and galactic assembly had proceeded much more rapidly than anyone had thought possible. It is likely that astronomers will find many such luminous galaxies, possibly at even earlier times, over the next decade with Webb. The James Webb Space Telescope was just beginning to explore the deepest reaches of space and time. Every major scientific theory rests on a foundation of carefully constructed models that predict how the universe should behave. When observations consistently contradict these predictions, scientists face a fundamental choice: modify the models or question whether something deeper is wrong with our understanding of reality itself. Current theories of early star and galaxy formation are incomplete. The discovery of Jade's GS Z14-0 and its bright companions was forcing astronomers to confront this uncomfortable truth. Decades of theoretical work had painted a picture of gradual cosmic evolution, but the universe was revealing a much more dramatic and rapid development. The spectroscopic confirmation of this source indicates the existence of many similar galaxies, particularly when considering the relatively small survey area of Jade's. This was not just one anomalous object that could be explained away as a special case. It was evidence of a systematic underestimation of how quickly the early universe could assemble complex structures. Consider a computer simulation designed to predict how a city will grow over time. If the simulation consistently predicts slow, gradual development, but satellite images reveal massive skyscrapers appearing in just the first few months, the underlying assumptions about construction rates and urban planning would need to be completely reconsidered. Cosmological models faced a similar crisis. The halo mass threshold required to yield a fixed moving abundance varies as the inverse sixth power of 1 plus redshift for this region of mass and redshift. In simpler terms, the dark matter structures needed to host such massive galaxies should have been extremely rare at such early times. Dark matter halos provide the gravitational scaffolding upon which galaxies form. These invisible structures must grow to a sufficient size before they can begin efficiently converting gas into stars. According to standard models, the early universe should not have had enough time to grow halos massive enough to support the bright galaxies Webb was discovering. Jade's GS Z14-0 represents a fascinating, yet very challenging test case for the scenario that astronomers had developed to explain galaxy formation. The galaxy exhibited properties that stretched multiple theoretical frameworks to their breaking points. The crisis extended beyond just galaxy formation models. If the early universe was more structured and active than predicted, it might indicate problems with our understanding of dark matter, dark energy, or even the fundamental physics governing cosmic expansion. If galaxies like Jade's GS Z14-0 existed in greater numbers, formed stars faster, and were chemically richer than we thought possible, what else are we missing? This question hung over the astronomical community like a storm cloud, suggesting that the discoveries might be symptoms of much deeper misunderstandings. Some theoretical physicists began to propose radical solutions. Perhaps the universe itself was not what it seemed to be. Perhaps the very stage upon which cosmic evolution played out was fundamentally different from what we had assumed. The discovery of Jade's GS Z14-0 marked the beginning of a cosmic treasure hunt that would reshape our understanding of the universe's earliest chapters. The astronomers agree that JWST's power has not yet reached its limits. None of them would be surprised if the telescope unveils a new redshift record within the year. The James Webb Space Telescope was operating like a time machine, systematically pushing back the boundaries of observable cosmic history. Astronomers realized they were standing at the edge of a new frontier. Every observation session brought the possibility of finding even more distant, even more impossible galaxies. This specific area Jades has been studying is pretty small. There are larger areas of the sky that have yet to be explored that maybe have even brighter and more distant galaxies. Picture archaeologists who had spent decades carefully excavating what they thought was a small, ancient settlement, only to discover that they were standing on the edge of a vast, buried metropolis. The scope of their task had suddenly expanded beyond anything they had imagined. Jade's GS C14-0 was the record holder at a redshift of 1432. But now, another ancient, bright galaxy has been found at a redshift of 14444, less than a year after the first discovery. An even more distant galaxy had been confirmed, pushing the cosmic frontier back by another 10 million years. This new record holder demonstrated that the pattern of unexpectedly bright early galaxies was not a fluke. This finding is surprising because astronomers expected to find very few galaxies at such a high redshift. Each new discovery reinforced the growing evidence that the early universe was far more active than anyone had predicted. The search was expanding beyond single telescope observations. Teams of astronomers around the world were coordinating efforts, sharing data, and developing new techniques to probe even deeper into cosmic time. Advanced computer algorithms were being trained to identify candidate distant galaxies in the vast data sets that Webb was collecting. Later this decade, the Nancy Grace Roman Space Telescope will join JWST in scanning the early universe. Roman will cover much larger areas of the sky with incredible detail. The Roman telescope would complement Webb's deep but narrow view with a wider survey capability, potentially discovering hundreds or thousands of ancient, bright galaxies. Together, these space telescopes would create the most comprehensive census of the early universe ever attempted. Every new galaxy discovered would add another piece to the puzzle of how cosmic structures formed and evolved during the universe's youth. But the implications extended far beyond simple discovery. Each ancient galaxy was a laboratory for testing our understanding of physics under extreme conditions. The densities, temperatures, and energy scales present during the formation of these early objects pushed matter to its limits. JWST itself appears poised to drive a series of great expansions of the cosmic frontier. Previously unimaginable redshifts, approaching the era of the very first stars, no longer seem far away, while astronomers struggled to understand why ancient galaxies were brighter and more numerous than expected. A completely different mystery was emerging from the data. New research has uncovered an intriguing mystery that the majority of galaxies appear to be rotating in the same direction across vast regions of space. Galaxies seem to be spinning in a coordinated pattern, as if responding to some universal influence. In a truly random universe, galaxy rotations should be roughly evenly split between clockwise and counterclockwise directions when viewed from our perspective. Imagine throwing thousands of coins into the air and finding that 70% land heads up. Such a result would immediately suggest that either the coins are weighted or some external force is influencing their behavior. This is significant because in a truly random universe, galaxy rotations should be roughly evenly split between two directions. The discovery of a preferential rotation challenged one of the most fundamental assumptions in cosmology, that the universe is isotropic and homogeneous on large scales. Studies of large-scale cosmic structures suggest a certain alignment in the way galaxies are distributed and move, rather than being entirely random. This so-called cosmic anisotropy challenges the widely accepted cosmological principle, which assumes the universe is isotropic and homogeneous on large scales. The implications were staggering. If the universe has a preferred direction or axis, it would mean that space itself might have properties we had never suspected. Like discovering that what appeared to be a perfectly smooth sphere actually has subtle ridges or patterns that influence everything that moves across its surface. Some researchers propose that this cosmic choreography might be evidence of rotation in the universe itself. If space-time possesses some form of overall angular momentum, it could impart a slight preference for rotational direction to the galaxies that form within it. If the universe does have a preferred direction, it could point to unknown physics at play, possibly related to the way our universe formed inside a black hole, or how fundamental forces interact on the grandest scales. The discovery was opening doors to exotic physics that operated on scales beyond anything we could directly test in laboratories. Alternative explanations were equally mind-bending. Perhaps the observed patterns were fossil remnants of processes that occurred during cosmic inflation, the theoretical period of rapid expansion that occurred in the universe's first fraction of a second. Or maybe they reflected the influence of dark matter structures that we could not directly observe. When matter collapses under gravity to form a black hole, it creates an event horizon, a boundary beyond which nothing can escape, not even light. Some physicists were beginning to wonder whether the coordinated galactic rotation might be evidence that our entire universe exists within such a boundary. Deep within the mathematics of general relativity lies a possibility so strange that most physicists had dismissed it as a mere curiosity. What if our entire universe exists inside a black hole? Some scientists interpreting the data have proposed something bold, that our entire universe might exist inside a black hole. This radical hypothesis, known as black hole cosmology, suggests that everything we observe, from distant galaxies to our own solar system, exists within the event horizon of a massive black hole in a larger parent universe. The theory emerged from attempts to reconcile the strange properties of the Big Bang with the physics of black holes. The Standard Model tells us that the universe began as a singularity, a point of infinite density, just like the center of a black hole. Both scenarios involve matter compressed to impossible densities under the influence of extreme gravitational fields. If our universe is actually the interior of a black hole that formed in a larger parent universe, it would mean that the Big Bang was not an explosion in empty space, but rather the moment matter collapsed into a black hole, creating a new universe inside. This would transform our understanding of cosmic origins from a mysterious beginning to a natural consequence of gravitational collapse in a higher dimensional reality. Consider the mathematical elegance of this possibility. Every property that makes our universe seem special, from its expansion rate to the values of the fundamental constants, could be natural consequences of existing within a black hole's interior. The apparent fine-tuning that allows complex structures like stars and galaxies to form might simply reflect the physics of black hole formation. Each and every black hole in our universe could be the doorway to another baby universe. This would create a fractal cosmos, where universes give birth to universes through the formation of black holes. Each new universe potentially developing its own physics and evolutionary timeline. The theory offered elegant explanations for several cosmic puzzles. Black holes are known to have immense entropy, which corresponds to the vast amount of information contained in our universe. The connection between entropy and information could help resolve paradoxes about what happens to information that falls into black holes. Even more intriguingly, the coordinated rotation of galaxies that astronomers were discovering could be a natural consequence of existing within a rotating black hole. If true, this could mean that instead of collapsing into an infinitely small point, a black hole could experience a big bounce, where the core rebounds and expands outward. potentially giving rise to a new universe inside. The mathematics suggested that quantum effects might prevent the formation of true singularities, causing collapsing matter to rebound and expand into new space-time regions. The scientists continued by adding that the rapid recoil after such a big bounce could be what has led to our expanding universe, an event we now refer to as the Big Bang. If our universe truly exists within a black hole, then every black hole we observe might be a doorway to an entirely new cosmos, complete with its own physics, planets, and perhaps even life. This theory would drastically change our understanding of cosmic origins, suggesting that the cycle of universes is an ongoing, self-replicating process. Instead of a single universe that appeared from nothing, we might inhabit one branch of an infinite cosmic tree, where each black hole represents both an ending and a beginning. Picture a vast cosmic ecosystem where universes reproduce through gravitational collapse. Just as biological organisms pass genetic information to their offspring, parent universes might transmit physical laws and constants to their cosmic children through the formation of black holes. This could explain why the fundamental forces in our universe seem precisely calibrated to allow complex structures to emerge. This could also explain why the fundamental constants of nature appear fine-tuned for life, because black holes that create stable universes may be more likely to persist and reproduce through this process. Universes with physics that promote stable star formation and complex chemistry would be more likely to produce the black holes necessary for cosmic reproduction. The implications were staggering. Every time a massive star collapses in our universe, it might be giving birth to a new cosmos containing billions of galaxies, each with their own planets and possibilities for life. The stellar death that marks an ending in our universe could simultaneously represent the Big Bang of another reality. This cosmic reproduction cycle would operate on timescales that dwarf biological evolution. While life on Earth has evolved over billions of years, cosmic evolution would unfold over trillions of generations of universe formation and development. Each new universe would be a cosmic experiment, testing slightly different combinations of physical laws and constants. The black hole universe theory also offered a potential resolution to the horizon problem in cosmology. Our universe appears remarkably uniform in temperature and structure across regions that should never have been in causal contact. If our cosmos began as the interior of a pre-existing black hole, this uniformity could be inherited from the parent universe's properties. Some theories suggest that this twisting effect of space-time could generate a repulsive force at extremely high densities, potentially preventing singularities from forming. Quantum mechanical effects operating at the smallest scales might create the cosmic bounce that transforms gravitational collapse into universal expansion. The mathematics of this process remained challenging, but the conceptual framework was elegant. Instead of a singularity exploding from nothing, it could have been a rebirth from the core of a black hole in a parent universe. Our Big Bang would be just one moment in an endless cycle of cosmic death and rebirth. Standing at the edge of cosmic understanding, astronomers find themselves equipped with tools powerful enough to peer back to the very dawn of time, yet humble enough to realize how much remains unknown. If it survives repeated cancellation threats, the Roman Space Telescope should reveal hundreds more of these types of galaxies. The future of cosmic archaeology depends not just on technological advancement, but on humanity's commitment to exploring the deepest questions about our existence. The Nancy Grace Roman Space Telescope, with its wide field capabilities, will complement the James Webb Space Telescope's deep but narrow view. Together, these instruments will conduct the most comprehensive survey of the early universe ever attempted. Where Webb finds individual ancient galaxies with exquisite detail, Roman will map their distribution across vast regions of space. A larger data set is always desirable and would help solidify some of these findings, or maybe introduce new mysteries. Science advances through the accumulation of evidence, but it also thrives on the discovery of new puzzles that challenge existing theories. The statistical power of hundreds or thousands of early galaxy observations will allow astronomers to test whether the current discoveries represent genuine departures from theoretical predictions or simply the extreme tail of expected distributions. More data will either confirm that galaxy formation proceeded much more rapidly than predicted or reveal new physics operating in the early universe. But the implications extend far beyond astronomy. The universe is turning out to be far stranger than we ever imagined. And the uneven galactic rotations will likely prompt astrophysicists to reassess certain aspects of our understanding of the universe. Each new discovery forces us to question assumptions we thought were rock solid. The coordinated rotation of galaxies across cosmic distances might indeed point to our universe existing within a larger structure. Or it might reveal new physics operating on scales we can barely comprehend. Either possibility would fundamentally change how we understand our place in the cosmic hierarchy. Maybe some earlier measurements of our universe are incorrect, especially the speed at which the Milky Way galaxy rotates. Sometimes, revolutionary discoveries turn out to have more mundane explanations, but the process of investigating them always advances our knowledge. Future observations will probe even deeper into cosmic time, perhaps eventually reaching the era when the very first stars ignited in the primordial darkness. These population 3 stars, composed only of hydrogen and helium, would have been massive giants that lived brief but spectacular lives, seeding space with the heavier elements necessary for planets and life. Scientists using Webb to study GNZ11 have also uncovered some tantalizing evidence for the existence of population 3 stars nestled in the outskirts of this remote galaxy. The discovery of these primordial stars would complete our picture of how the universe transitioned from simplicity to complexity. Supermassive black holes, with masses millions or billions of times greater than our sun, typically power the brightest objects in the universe. These cosmic engines devour gas and dust, heating material to millions of degrees and launching it outward in brilliant jets of plasma. When astronomers spot an exceptionally bright galaxy, they usually expect to find one of these giants lurking at its center. Jade's GS Z14-0 defied this expectation completely. From the images, the source is found to be over 1,600 light-years across, proving that the light we see is coming mostly from young stars and not from emission near a growing supermassive black hole. The galaxy's brightness was not the product of a feeding black hole, but rather an explosive nursery of newborn stars. This absence created a cosmic puzzle. Most galaxies that shine this brightly rely on the intense radiation generated by matter spiraling into a supermassive black hole. These black holes act like cosmic lighthouses, often outshining all the stars in their host galaxies combined. But Jade's GS Z14-0 was generating its tremendous luminosity through pure stellar formation. Think of it like discovering a medieval village that somehow produces the same amount of light as a modern city, but without any electrical power. The village would need to have an impossibly large number of torches and fires burning simultaneously. Similarly, this ancient galaxy needed to be forming stars at a rate that seemed almost impossible for its era. The galaxy has a star formation rate, averaged over the last 10 million years, of approximately 22 solar masses per year. That means every single year, this galaxy converts material equivalent to 22 suns into newborn stars. For such a young cosmic age, this rate represents a stellar baby boom of unprecedented proportions. The implications stretch far beyond this single galaxy. Supermassive black holes are thought to play crucial roles in regulating star formation throughout their host galaxies. They can both trigger star birth by compressing gas clouds and halt it by blowing material away with powerful winds. Without a central black hole, how is this galaxy managing to form stars so efficiently? Even more puzzling, most theoretical models suggest that supermassive black holes and their host galaxies grow together over cosmic time. The absence of a detectable black hole in such a massive early galaxy challenged this fundamental relationship. All of these observations, together, tell us that Jade's GS-Z14-0 is not like the types of galaxies that have been predicted by theoretical models and computer simulations to exist in the very early universe. It was operating by rules we had not yet discovered, hidden in the outskirts of ancient galaxies. Astronomers are searching for the universe's very first stars. These elusive objects, known as Population 3 stars, would have been the cosmic pioneers that brought light to a universe filled only with hydrogen and helium. No definitive detection of such stars has ever been made. But scientists know they must exist. Now, with Webb, their discovery seems closer than ever before. Scientists using Webb to study another ancient galaxy have also uncovered some tantalizing evidence for the existence of Population 3 stars nestled in the outskirts of this remote galaxy. These primordial giants would have been fundamentally different from any star we observe today, composed entirely of the simplest elements forged during the Big Bang. Picture the universe in its first 100 million years as a vast, dark ocean punctuated by islands of light. Population 3 stars would have been these first beacons, massive beyond anything we see in the modern cosmos. Without heavier elements to help them radiate energy efficiently, these stars would have grown to enormous sizes, perhaps 50 to 100 times more massive than our Sun. Their lives would have been spectacular, but brief, burning through their nuclear fuel in just a few million years. These stellar giants would have ended their existence in catastrophic explosions that scattered the first heavy elements across space. Carbon, oxygen, nitrogen, and iron, forged in their nuclear furnaces, would become the building blocks for the next generation of stars, and eventually for planets and life itself. The search for Population 3 stars represents one of astronomy's greatest challenges. These objects existed so long ago that their light has been traveling for over 13 billion years to reach us. Even the most powerful telescopes struggle to detect individual stars at such extreme distances. But Webb's infrared vision offers new hope. When Population 3 stars exploded as supernovas, they would have created distinctive signatures in the surrounding gas clouds. These fingerprints might still be visible today, encoded in the light from galaxies that formed in regions enriched by the first stellar explosions. Looking deeply into space and time, two teams using NASA's James Webb Space Telescope have studied the exceptionally luminous galaxy, which existed when our 13.8 billion-year-old universe was only about 430 million years old. This galaxy shows chemical patterns that might reflect the influence of Population 3 stellar explosions. A second team used Webb's near-infrared spectrograph to find a gaseous clump of helium in the halo surrounding this ancient galaxy. Pure helium clouds are exactly what astronomers would expect to find if Population 3 stars had recently exploded nearby, seeding space with their nuclear products while leaving behind pockets of pristine, primordial gas. The discovery of these cosmic fossils would complete our understanding of how the universe transitioned from darkness to light. Population 3 stars were the match that lit the cosmic candle. beginning the long chain of stellar evolution that eventually led to our solar system. Each ancient galaxy discovered by Webb brings us closer to finding direct evidence of these first stars. Every element heavier than hydrogen and helium tells a tale of stellar alchemy, of massive stars that lived, died, and scattered their nuclear products across space. This cosmic recycling program transformed a universe of simple gases into one capable of supporting rocky planets, organic molecules, and eventually, life itself. When astronomers examine the light from Jade's GS Z14-0 and other ancient galaxies, they are reading the chemical diary of the early universe. Each emission line in their spectra represents a different element, and the relative intensities reveal how much of each element was present when that light was emitted. The nitrogen abundance in these early galaxies presents a cosmic puzzle that challenges our understanding of stellar evolution timescales. Nitrogen is primarily produced inside intermediate mass stars through a complex series of nuclear reactions that typically require hundreds of millions of years to complete. Yet these galaxies existed when the universe was barely 300 million years old. For them to show significant nitrogen enrichment, stellar evolution must have proceeded much more rapidly than our current models predict, or entirely different physical processes were at work in the early cosmic environment. This chemical fingerprint matches what we see in some of the oldest star clusters orbiting the Milky Way, suggesting that similar physical conditions existed both in the early universe and in the dense environments where globular clusters form. The connection implies that we might be observing universal principles of star formation operating under extreme conditions. The implications extend far beyond individual galaxies. If chemical evolution proceeded rapidly throughout the early universe, it would mean that the building blocks for complex chemistry became available much sooner than previously thought. Rocky planets could have formed earlier. Organic molecules could have emerged sooner. And the window for life to develop would have opened billions of years ahead of schedule. Consider the profound philosophical implications. If the universe became chemically mature much earlier than we believed, then Earth-like worlds, and potentially life itself, might have had far more time to develop and evolve. We might be late arrivals to a cosmic party that has been ongoing for much longer than anyone imagined. The rapid chemical enrichment also suggests that feedback processes between stars and their surrounding gas operated differently in the early universe. Stellar winds and supernova explosions would have mixed freshly synthesized elements through space more efficiently, accelerating the pace of cosmic evolution. Furthermore, as noticed by recent studies, these morphological differences are reflected in chemical abundance patterns, signaling a deeper connection between galaxy structure and evolutionary pathways. Compact galaxies tend to show different chemical signatures than extended ones, suggesting that physical size and chemical evolution are intimately linked. The universe was conducting chemistry experiments on a cosmic scale, testing different combinations of stellar masses, formation rates, and environmental conditions. Each ancient galaxy represents a different outcome of these experiments. Invisible scaffolding shapes everything we see in the universe. Yet the discovery of impossibly early, massive galaxies suggests this cosmic architecture might work differently than we thought. Dark matter. The mysterious substance that comprises over 80% of all matter in the universe provides the gravitational framework upon which galaxies form. According to our best theories, ordinary matter falls into dark matter halos, accumulating until it reaches the critical density needed to ignite star formation. This process should take time, lots of time. Dark matter halos must grow through countless mergers and accretion events before they become massive enough to host the bright galaxies that Webb is discovering. The standard model of cosmic structure formation predicts that truly massive halos should have been extremely rare in the first few 100 million years after the Big Bang. Yet Jade's GS-Z14-0 and its companions exist in apparent defiance of these predictions. The halo mass threshold required to yield a fixed come-moving abundance varies as the inverse sixth power of 1 plus redshift for this region of mass and redshift. In simpler terms, the dark matter structures needed to support such massive early galaxies should have been vanishingly rare. Think of it like finding skyscrapers in a city that was supposedly founded just last week. The construction requires not just time, but also the development of sophisticated infrastructure, supply chains, and engineering expertise. Similarly, massive galaxies require mature dark matter halos that should not have existed so early in cosmic history. From a theoretical simulation, we estimate that the probability of finding halos massive enough to host these bright early galaxies was incredibly low. The simulations suggest we should have found perhaps one such object in the entire observable universe, not dozens scattered across Webb's relatively small survey areas. This discrepancy points to several possible explanations, each with profound implications for our understanding of cosmic evolution. Perhaps dark matter behaves differently than we assumed, interacting with itself or with ordinary matter in ways that accelerate halo formation. Or maybe the relationship between halo mass and galaxy brightness is not what our models predict. Alternative theories propose that dark matter might have additional properties that become important in the extreme conditions of the early universe. Self-interacting dark matter, for instance, could undergo rapid collapse and rebound cycles that efficiently concentrate mass into the cores of halos. Another possibility is that early star formation was far more efficient than current models suggest. If the first stars could form with much less dark matter support than is required today, then bright galaxies could appear in smaller halos that were more common in the early universe. The puzzle deepens when we consider that these early galaxies show evidence of multiple generations of stellar evolution. Not only did they form earlier than expected, but they also evolved faster, cycling through stellar birth and death at an accelerated pace that compressed billions of years of evolution into a few hundred million. In the cosmic dance between stars and galaxies, energy flows in both directions, creating feedback loops that should regulate and limit how quickly galaxies can grow. When massive stars explode as supernovas, they release tremendous amounts of energy that heats the surrounding gas and blows it away from the galaxy. This process, known as stellar feedback, acts like a cosmic thermostat, preventing galaxies from forming stars too quickly and burning through their gas reserves. Similarly, when gas falls into supermassive black holes, it generates powerful winds and jets that can clear entire galaxies of star-forming material. These feedback mechanisms are thought to be essential for explaining why galaxies do not convert all of their available gas into stars within the first few million years of their existence. Yet the ancient galaxies discovered by Webb seem to have bypassed these cosmic speed limits entirely. Jade's GS-Z14-0 shows evidence of vigorous star formation occurring at rates that should have triggered feedback processes strong enough to shut down further stellar birth. The galaxy exhibits properties that stretched multiple theoretical frameworks to their breaking points. Its high star formation rate, combined with its large stellar mass, suggests that feedback mechanisms were either much weaker in the early universe, or that these galaxies had access to continuous supplies of fresh gas to fuel their incredible growth. Consider the energy budget involved. Every time a massive star explodes, it releases energy equivalent to our sun's entire lifetime output in just a few seconds. Multiple supernovas exploding within a small galaxy should create a devastating storm of hot gas and radiation that prevents new stars from forming for millions of years. But these early galaxies appear to have weathered such cosmic storms without interruption, Some theoretical models suggest that the dense environment of the early universe might have allowed galaxies to retain their gas despite energetic feedback processes. The rapid chemical enrichment observed in these galaxies provides additional evidence that stellar feedback was not effectively removing freshly synthesized elements from star-forming regions. Instead of being blown away by stellar winds, heavy elements were apparently retained and incorporated into subsequent generations of stars. This retention of metals and gas implies that early galaxies were more efficient at converting raw materials into stars than their modern counterparts. The physics of star formation itself might have operated differently when the universe was young and dense. Another possibility is that these galaxies were fed by continuous streams of pristine gas falling in from the cosmic web. If the accretion rate was high enough, it could overwhelm the feedback processes and maintain a steady rate of star formation despite ongoing stellar explosions. The crisis in feedback theory extends beyond individual galaxies to cosmic evolution as a whole. If early galaxies could grow without the regulatory mechanisms that govern modern star formation, then the entire timeline of cosmic structure formation might need to be reconsidered. Stretching across billions of light years, an invisible network of dark matter filaments connects galaxies throughout the universe, forming the cosmic web that defines large-scale structure. This vast scaffolding channels gas and dark matter along preferred pathways, feeding material to galaxies at the intersections where filaments meet. The cosmic web grows gradually over time, with the most massive structures forming at the nodes where multiple filaments converge. According to standard models, the early universe should have had only the most rudimentary web structure. The first few 100 million years after the Big Bang would have been dominated by small-scale fluctuations, with large-scale organization developing slowly as gravity amplified the tiny density variations left over from cosmic inflation. Yet the discovery of numerous bright galaxies at extreme distances suggests that the cosmic web was already remarkably well developed when the universe was barely 300 million years old. These galaxies appear to be located at the major intersections of dark matter filaments, implying that large-scale structure formation proceeded much more rapidly than predicted. If the universe does have a preferred direction, it could point to unknown physics at play, possibly related to the way our universe formed inside a black hole, or how fundamental forces interact on the grandest scales. Studies of large-scale cosmic structures suggest a certain alignment in the way galaxies are distributed and move, rather than being entirely random. This cosmic anisotropy challenges the widely accepted cosmological principle, which assumes the universe is isotropic and homogeneous on large scales. Picture the cosmic web as a three-dimensional spiderweb spanning the entire observable universe. In the standard picture, this web should have been sparse and incomplete during the cosmic dawn, with only small sections connected to each other. Instead, observations suggest that the major highways of the cosmic web were already in place, efficiently channeling material to the galaxy formation sites. The implications are staggering. If large-scale structure formation proceeded much faster than our models predict, it might indicate that dark matter and dark energy behave differently than we assume, or that additional physical processes were at work during the universe's earliest epochs. Alternative explanations invoke exotic physics operating during cosmic inflation. Perhaps the quantum fluctuations that seeded cosmic structure were not as random as we believed, but instead carried subtle patterns that accelerated the formation of these large-scale networks. Another possibility is that the cosmic web itself influences galaxy formation in ways we have not fully understood. Rather than simply providing the scaffolding for galaxy assembly, the web might actively channel energy and matter in patterns that enhance the efficiency of star formation. The discovery of bright early galaxies at what appear to be the nodes of the cosmic web suggests that the relationship between large-scale structure and galaxy formation was already well established when the universe was remarkably young. One of cosmology's most enduring puzzles concerns how the universe achieved such remarkable uniformity across regions that should never have been in causal contact. The cosmic microwave background radiation, the afterglow of the Big Bang, shows the same temperature to within 1 part in 100,000 across the entire sky. This uniformity extends to regions separated by distances so vast that light has not had time to travel between them since the universe began. How can regions that have never exchanged information display such identical properties? This horizon problem has plagued cosmologists for decades, leading to the development of the cosmic inflation theory as a proposed solution. Inflation suggests that the universe underwent a brief period of exponential expansion in its first fraction of a second, stretching tiny, causally connected regions to cosmic scales. This would explain how distant parts of the universe share the same temperature and other properties. But the discovery of impossibly bright and massive galaxies in the cosmic dawn adds a new dimension to the horizon problem. These objects appear to have formed too quickly and grown too large for the available time, suggesting that the early universe was more interconnected and organized than the standard model allows. If our cosmos began as the interior of a pre-existing black hole, this uniformity could be inherited from the parent universe's properties. The horizon problem would dissolve because our universe would have inherited its uniform properties from a larger, already connected system. This black hole cosmology offers an elegant resolution to several cosmic puzzles simultaneously. The Big Bang would not represent the beginning of time, but rather a phase transition from gravitational collapse to expansion, carrying forward the organized properties of the parent universe. Consider the implications for early galaxy formation. If our universe inherited large-scale structure from its parent, then the cosmic web could have been partially assembled from the very beginning. This would explain how massive galaxies could form so quickly, in apparent violation of the bottom-up structure formation models. The coordinated rotation of galaxies across cosmic distances might be another inherited property, reflecting an angular momentum present in the parent universe at the time of black hole formation. Instead of emerging randomly from quantum fluctuations, large-scale patterns could be the fossil remnants of the parent cosmos. Recent observations of cosmic anisotropy, where galaxies show preferred orientations across vast regions of space, support the idea that the universe possesses large-scale, coherent properties that extend beyond what inflation alone can explain. If these patterns represent inherited characteristics from a parent universe, then many aspects of cosmic evolution that seem fine-tuned or improbable might actually be the natural consequences of our universe's nested origin within a larger cosmological system. The horizon problem, long considered evidence for exotic physics during cosmic inflation, might instead point toward an even more exotic possibility that our universe is one of countless cosmic offspring, each inheriting its properties from its parent through the formation of black holes. The fundamental constants of nature appear to be precisely calibrated to allow the existence of stars, planets, and life, a phenomenon that has puzzled scientists for generations. Change the strength of the strong nuclear force by just a few %, and atomic nuclei would not be stable. Alter the ratio of the electron and proton masses slightly, and chemistry as we know it would be impossible. Adjust the cosmological constant that drives cosmic expansion, and galaxies might never form or might fly apart before stars can ignite. This apparent fine-tuning has led to intense debates about why our universe seems so perfectly suited for complexity in life. Some invoke the anthropic principle, arguing that we observe these values simply because we exist to observe them. Others propose the existence of multiple universes with different physical laws, making our life-friendly cosmos just one possibility among countless others. But the black hole universe theory offers a radically different perspective on this fine-tuning. This could also explain why the fundamental constants of nature appear fine-tuned for life, because black holes that create stable universes may be more likely to persist and reproduce through this process. Imagine cosmic evolution as a vast reproductive process, where universes that develop stable physics are more likely to create the black holes necessary for producing offspring universes. Over countless generations of cosmic reproduction, natural selection would favor physical constants that promote complexity, structure formation, and long-term stability. Universes with physics that promote stable star formation and complex chemistry would be more likely to produce the black holes necessary for cosmic reproduction. Those with constants that prevent galaxy formation or cause rapid collapse would be evolutionary dead ends, unable to propagate their physical laws to future generations. This cosmic natural selection would explain not only why our universe supports complexity, but also why the early galaxies discovered by Webb show such sophisticated chemical evolution. If our cosmos inherited its physics from a long lineage of successful parent universes, then rapid structure formation and efficient star formation might be deeply embedded characteristics. The fine-tuning paradox dissolves when viewed through this reproductive lens. Rather than being improbably perfect by chance or by design, our universe's properties would be the product of eons of cosmic evolution, refined through countless cycles of birth, development, and reproduction. Each generation of universes would inherit the successful physical constants of their parents, while potentially introducing small variations through the quantum mechanical processes operating during black hole formation. Over cosmic time, this would lead to the gradual optimization of physical laws for promoting complexity and longevity. The apparent youth and sophistication of the early galaxies fits naturally into this framework. If our universe descended from a long line of successful parent cosmos, it would have inherited not just fine-tuned constants, but also the capacity for rapid and efficient structure formation. Deep within the mathematics of black hole physics lies one of the most profound puzzles in modern science. What happens to information when it falls beyond the event horizon? According to quantum mechanics, information cannot be truly destroyed. Every particle, every quantum state, every bit of data about the physical world must be preserved in some form, even if it becomes impossible to access or decode. Yet black holes appear to violate this fundamental principle. When matter falls into a black hole, it seems to vanish from our universe completely, taking with it all the information about its quantum states, its history, and its properties. Stephen Hawking showed that black holes eventually evaporate through thermal radiation. But this radiation appears to carry no information about what fell in, creating an apparent paradox. But if our universe exists within a black hole, this paradox takes on a new and profound significance. Black holes are known to have immense entropy, which corresponds to the vast amount of information contained in our universe. Every star, planet, atom, and quantum state in our cosmos would contribute to the total information content stored within the black hole that contains us. This connection offers a potential resolution to the information paradox. Rather than being destroyed, the information that falls into black holes might give birth to new universes, each one encoding and preserving the quantum states that entered the black hole. The information would not be lost, but transformed into the initial conditions for a new cosmic system. Consider the staggering implications. Every black hole in our universe might contain not just compressed matter, but entire cosmological systems with their own galaxies, stars, and potentially life. The black holes we observe through our telescopes could be windows into countless other realities, each one as vast and complex as our own. This nested structure would create a cosmic library of unimaginable scale, where information is preserved across multiple levels of reality. The quantum states that fell into ancient black holes in parent universes might be encoded in the fundamental constants and initial conditions of our cosmos. The rapid formation of complex galaxies in our early universe might reflect information inherited from previous cosmic generations, rather than starting from simple initial conditions. Our universe could have begun with sophisticated organizational templates encoded in its basic structure. Each ancient galaxy discovered by Webb would represent not just early star formation, but the expression of cosmic information patterns inherited from parent universes. The chemical complexity, the structural organization, and the rapid evolution of these galaxies might be the manifestations of information processing operating on cosmological scales. If black holes preserve and transform information rather than destroying it, then every supermassive black hole in our universe serves as both an ending and a beginning. A cosmic recycling center where the information content of one reality becomes the foundation for new cosmic systems. At the heart of every black hole lies a mystery that challenges our understanding of space, time, and the fundamental nature of reality itself. Classical physics predicts that matter falling into a black hole will collapse into a singularity, a point of infinite density where the laws of physics break down completely. But quantum mechanics suggests a different fate, one that could transform cosmic death into cosmic birth. Some theories suggest that this twisting effect of space-time could generate a repulsive force at extremely high densities, potentially preventing singularities from forming. Instead of crushing matter into mathematical points, quantum effects might create a cosmic bounce that rebounds outward, giving birth to new, expanding universes. This quantum bounce mechanism operates through the inherent uncertainty principles that govern matter at the smallest scales. When particles are compressed to densities approaching the Planck scale, quantum fluctuations become so intense that they generate an outward pressure strong enough to halt and reverse the gravitational collapse. Picture a cosmic trampoline stretched to its absolute limit. Just as a ball dropped onto a trampoline will bounce back upward if the elastic force exceeds the downward momentum, matter collapsing into a black hole might rebound when quantum pressure overcomes the gravitational attraction. The scientists continued by adding that the rapid recoil after such a big bounce could be what has led to our expanding universe, an event we now refer to as the Big Bang. Instead of a singularity exploding from nothing, it could have been a rebirth from the core of a black hole in a parent universe. This mechanism would explain many of the puzzling features of our universe's early evolution. The rapid formation of large-scale structures, the sophisticated chemistry of early galaxies, and the apparent fine-tuning of physical constants could all be inherited characteristics from the parent universe, transmitted through the quantum bounce process. If true, this could mean that instead of collapsing into an infinitely small point, a black hole could experience a big bounce where the core rebounds and expands outward, potentially giving rise to a new universe inside. The process would conserve information while transforming it into new forms of cosmic organization. The quantum bounce would not be instantaneous, but might occur over cosmic timescales from the perspective of the new universe. What appears as the Big Bang and subsequent cosmic evolution to us might represent the gradual expansion following the quantum rebound of matter in a parent universe's black hole. This process could operate recursively, with each new universe capable of forming its own black holes and spawning additional cosmic offspring. The result would be an infinite, fractal structure where universes give birth to universes through cycles of collapse and quantum rebound. The early galaxies discovered by Webb might be direct evidence of this process at work. Their rapid formation and sophisticated properties could reflect the efficient transfer of organizational information from a parent to an offspring universe through the quantum bounce mechanism. Each black hole in our cosmos would be both a cosmic endpoint and a cosmic beginning, transforming the matter and information of our universe into the seeds of new realities through the mysterious quantum processes that operate at the intersection of gravity and quantum mechanics. If our universe exists within a black hole, then we must confront the possibility that reality is organized as an infinite hierarchy of nested cosmic systems. Every black hole we observe, from stellar mass objects to the supermassive giants at galaxy centers, could contain entire universes with their own galaxies, stars, planets, and potentially life. This would create a cosmic matryoshka doll of staggering proportions, where each level of reality contains countless sub-levels, extending downward into infinity. Consider the scale relationships involved. A supermassive black hole in our universe might contain a cosmos with billions of galaxies, each hosting billions of stars. Some of those stars would form their own black holes, creating additional layers of nested reality. The recursive structure would continue indefinitely, with no fundamental limit to the depth of cosmic organization. From our perspective, we occupy one specific level in this hierarchy. We can observe black holes that might contain entire universes, but we cannot directly communicate with or influence those nested realities. Similarly, if our universe exists within a black hole in a parent cosmos, the inhabitants of that larger reality would be unable to directly observe or interact with us. This cosmic hierarchy would operate according to fundamental principles of information, preservation, and transformation. Each level would inherit properties from its parent, while developing its own unique characteristics through the processes of cosmic evolution. The rapid formation of complex structures in our early universe might reflect our position in this hierarchy. If our cosmos inherited organizational templates from a parent universe, then sophisticated galaxy formation could proceed much more efficiently than models based on starting from simple initial conditions predict. Each new level of the hierarchy would represent a different scale of cosmic organization. Just as atoms combine to form molecules, molecules form cells, and cells form organisms. Universes might combine to form larger-scale structures that we cannot currently imagine or detect. The hierarchy might extend upward as well as downward. Our parent universe could itself be nested within an even larger cosmic system, which in turn exists within another level of reality. The ultimate structure could be infinite in both directions, with no fundamental top or bottom to the cosmic organization. This perspective transforms our understanding of cosmic significance. Rather than being isolated observers in a unique universe, we would be participants in an infinite network of cosmic consciousness, each level contributing to the overall complexity and information content of the universal hierarchy. The black holes we study with our telescopes would not be cosmic monsters devouring matter and energy, but cosmic wombs, nurturing new universes through their mysterious interiors. Each would represent a portal between different levels of reality, facilitating the flow of information and organization across cosmic scales. If every black hole contains a universe potentially harboring billions of intelligent civilizations, then consciousness might be far more abundant and significant in the cosmic scheme than we ever imagined. rather than being rare accidents in an otherwise lifeless cosmos. Thinking beings could be fundamental components of universal organization. Consider the information processing requirements of a nested universe system. Each level of the hierarchy would need to maintain, organize, and transform vast amounts of information as it inherits properties from parent universes and potentially gives birth to offspring cosmos. Consciousness might serve as the universe's method for processing and organizing this cosmic information. Intelligent civilizations could function as the universe's neurons, collecting data about their local cosmic environment, processing it through scientific observation and theoretical understanding, and potentially transmitting that information to other levels of the hierarchy through mechanisms we do not yet comprehend. The rapid development of complex structures in our early universe might reflect not just inherited physical organization, but inherited patterns of information processing. If parent universes develop sophisticated mechanisms for organizing matter and energy through the activities of conscious beings, these templates could be passed down to offspring cosmos. Each ancient galaxy discovered by Webb might represent not just stellar formation, but the emergence of information processing networks that will eventually give rise to consciousness and intelligence. The chemical complexity observed in these early systems provides the necessary building blocks for organic chemistry and, potentially, life. This perspective suggests that consciousness and cosmic evolution are intimately connected, rather than being separate phenomena. The development of intelligence and the organization of cosmic structure might be different aspects of the same fundamental process of universal information integration. The coordinated rotation of galaxies across vast distances might reflect large-scale information processing operating on cosmic scales. Just as neural networks in biological brains show coordinated activity patterns, galaxy networks might display similar coherence as they participate in universe-scale computational processes. If our universe exists within a black hole in a parent cosmos, then our scientific observations and theoretical understanding might be contributing to the information processing occurring at that higher level of organization. Our attempts to understand cosmic evolution could be part of the parent universe's effort to understand itself. Quantum mechanics tells us that the act of observation fundamentally changes the systems being observed, collapsing probability waves into definite states and determining the outcome of quantum measurements. But what if this observer effect operates on cosmic scales, with consciousness playing a fundamental role in determining the large-scale structure and evolution of the universe itself? If our universe exists within an infinite hierarchy of nested black hole cosmos, then conscious observers at each level might be actively participating in the creation and maintenance of reality at their scale. Our scientific observations and measurements could be helping to determine not just what we discover about the universe, but what properties the universe actually possesses. The anthropic principle suggests that we observe the universe to have properties compatible with our existence simply because we exist to observe them. But in a nested cosmic hierarchy, this relationship might be far more active and dynamic than previously imagined. Consider the implications for the ancient galaxies discovered by Webb. These objects formed when the universe was young and its properties were still stabilizing. The act of observing them now, billions of years after their formation, might be retroactively influencing their properties through quantum mechanical connections that operate across cosmic time. This would create a cosmic bootstrap paradox, where the universe develops properties that ensure the eventual emergence of observers capable of studying its early evolution. The observer effect would operate across space and time, creating self-consistent cosmic histories that support the development of consciousness. The rapid formation of complex structures in the early universe might reflect this observer-driven cosmic evolution. If consciousness at various levels of the cosmic hierarchy is actively participating in cosmic organization, then galaxy formation could proceed much more efficiently than purely physical processes would allow. Quantum entanglement might provide the mechanism for this cosmic scale observer effect. If particles and systems throughout the universe remain quantum mechanically connected across vast distances and timescales, then conscious observations anywhere in the cosmos could influence conditions everywhere else. The coordinated rotation of galaxies across cosmic distances might be evidence of this quantum entanglement operating on large scales. Rather than being independent systems, galaxies could be components of a vast quantum network, where measurement and observation at one location instantly affects conditions throughout the entire system. This perspective transforms scientific observation from passive data collection into active participation in cosmic creation. Every measurement we make, every theory we develop, every discovery we announce could be contributing to the ongoing process of universal self-organization. The nested universe hierarchy would amplify this effect across multiple levels of reality. Conscious observers in parent universes might be influencing the conditions in our cosmos, while our observations might be affecting the universes nested within the black holes in our local cosmic neighborhood. If our universe truly exists within a black hole in a larger parent cosmos, it raises a fascinating question about communication and information transfer between the different levels of the cosmic hierarchy. According to general relativity, nothing can escape from within a black hole's event horizon, including light, matter, and information. This would seem to make communication between nested universes impossible, trapping each cosmic level in complete isolation from its parents and its offspring. Yet the existence of organized structures and apparent fine-tuning in our universe suggests that information has somehow been transmitted from parent systems. The rapid formation of complex galaxies, the sophisticated chemistry of early star formation, and the coordinated patterns observed on cosmic scales all point to inherited organizational templates. The solution to this communication paradox might lie in the quantum mechanical nature of black hole formation and evolution. When a black hole forms through gravitational collapse, it does not instantly cut off all connection to the outside universe. Instead, the process of horizon formation and information encoding might allow for sophisticated transfer mechanisms operating through quantum entanglement. Hawking radiation provides one potential communication channel. As black holes slowly evaporate, they emit particles that might carry encoded information about the internal universe. From the perspective of the parent cosmos, this radiation could provide a slow but steady stream of data about the conditions within the nested universe. From our perspective within a black hole universe, we might be able to influence this communication channel through our collective activities as conscious observers. The development of advanced civilizations, the creation of complex technologies, and even the pursuit of scientific understanding might all contribute to information patterns that eventually influence the Hawking radiation emitted by our containing black hole. Consider the timescales involved. While communication through Hawking radiation would be extraordinarily slow from our internal perspective, it might operate efficiently from the viewpoint of the parent universe, where our entire cosmic history unfolds in a much shorter time frame due to relativistic effects. The coordinated galactic rotations observed across our universe might represent a form of cosmic scale information encoding. If consciousness throughout our cosmos collectively organizes matter and energy in specific patterns, these patterns could be transmitted to the parent universe through quantum mechanical channels we do not yet understand. Another possibility involves the moment of black hole formation itself. The initial conditions that gave birth to our universe might have been encoded with sophisticated information templates from the parent cosmos. Rather than requiring ongoing communication, all the necessary organizational information could have been transmitted during the quantum bounce that created our expanding space-time. The rapid evolution of the early galaxies discovered by Webb might be direct evidence of this encoded information being expressed. As our universe expanded and cooled, the inherited organizational templates would begin to manifest as complex structures, forming much more quickly than purely random processes would allow. This suggests that while we cannot send messages back to our parent universe in any conventional sense, our collective development as a cosmic system might be generating information patterns that influence the properties of our containing black hole. In essence, our universe's evolution could be a form of slow, cosmic-scale communication. As we stand at the threshold of discoveries that could revolutionize our understanding of reality itself, we must confront questions that stretch the boundaries of science, philosophy, and human comprehension. If our universe exists within an infinite hierarchy of nested black hole cosmos, what does this mean for the concepts of beginning and ending, of uniqueness and significance, of isolation and connection? The very foundations of how we think about existence might need to be rebuilt from the ground up. The discovery of impossibly bright and sophisticated galaxies in our cosmic dawn forces us to question whether we have fundamentally misunderstood the nature of time, causality, and cosmic evolution. Perhaps what we interpret as rapid galaxy formation is actually the expression of organizational patterns that transcend our local space-time. Inherited from parent universes through quantum mechanical processes we can barely imagine, the question echoes across cosmic scales. From individual human curiosity to universal self-inquiry. If consciousness plays a fundamental role in cosmic organization, then our wondering about these mysteries might be contributing to the universe's own effort to understand its place in the larger hierarchy of reality. The ancient galaxies that prompted this investigation might be more than just astronomical objects. They could be cosmic fossils, preserving information about our universe's ancestry, quantum archaeological artifacts that encode the history of how our reality inherited its properties from parent systems. Each discovery pushes us to confront the possibility that everything we thought we knew about cosmic uniqueness might be wrong. Rather than inhabiting a singular universe that began with the Big Bang and will end with heat death or collapse, we might be temporary participants in an infinite cycle of cosmic reproduction and evolution. The implications for human meaning and significance are profound. If our universe is one of countless nested realities, does this diminish our importance or enhance it? Are we cosmic accidents or essential components of universal self-organization? Do our lives and achievements matter only locally? Or do they contribute to information processing occurring on scales we cannot comprehend? The coordinated rotation of galaxies across cosmic distances might be evidence that we are already participating in forms of cosmic consciousness that operate beyond individual awareness. Our scientific discoveries, our technological achievements, and even our philosophical questioning might be contributing to patterns of cosmic organization that span multiple levels of the universal hierarchy. As astronomers continue to peer deeper into space and time with increasingly powerful instruments, they are simultaneously looking deeper into questions about the nature of reality itself. Each new ancient galaxy discovered represents not just another data point, but another piece of evidence that the universe is far stranger and more interconnected than our theories had suggested. The James Webb Space Telescope and its successors might be doing more than just studying distant objects. They might be facilitating communication between the different levels of cosmic organization, helping our universe to understand its place in the infinite hierarchy of nested realities. The ultimate questions are not just about what we will discover, but about how those discoveries will change our understanding of what it means to exist in a universe that might be far more alive, connected, and purposeful than we ever dared to imagine. Looking forward to the next decade of cosmic discovery, we find ourselves standing at the edge of what might be the greatest revolution in human understanding since we first realized that the Earth orbits the Sun. The Nancy Grace Roman Space Telescope, scheduled for launch later this decade, will survey vast areas of the sky with unprecedented depth and precision, where Webb has opened windows into individual ancient galaxies. Roman will map the cosmic landscape on scales that could reveal the true extent of early universe complexity. Together, these space-based observatories will create the most comprehensive census of the cosmic dawn ever attempted. If current trends continue, they may discover thousands of bright, early galaxies, each one potentially forcing further revisions to our models of cosmic evolution. The statistical power of such a large sample could finally determine whether we are witnessing genuine departures from theoretical predictions or simply the extreme but expected outcomes of known physical processes. But perhaps more importantly, these observations might reveal patterns that point toward the nested cosmic hierarchy that some theories now suggest. If galaxies show coordinated properties across vast distances and cosmic time, it could provide the first direct evidence that our universe participates in organizational structures that transcend our local spacetime. JWST itself appears poised to drive a series of great expansions of the cosmic frontier. Previously unimaginable redshifts, approaching the era of the very first stars, no longer seem far away. Each new discovery chips away at the assumption that our universe is an isolated system, revealing instead a cosmos that might be intimately connected to larger realities through quantum mechanical processes we are only beginning to understand. The search for population 3 stars continues, promising to reveal how the universe's first lights emerged from the primordial darkness. These cosmic pioneers could provide the missing link between the simple universe of the Big Bang and the complex chemistry required for planets and life. Advanced computer simulations running on the world's most powerful supercomputers are being designed to test whether the nested black hole universe theory can quantitatively explain the rapid formation of the early galaxies. If successful, these models could provide a new framework for understanding cosmic evolution that extends from the quantum scales to infinite hierarchies of nested realities. The implications reach far beyond astronomy. If our universe exists within a cosmic hierarchy, then every field of human knowledge, from physics to philosophy, from biology to consciousness studies, will need to be reconsidered in light of our interconnected cosmic status. Future generations might look back on this era as the moment when humanity first began to understand its true place in the infinite network of nested universes. The ancient galaxies that so surprised astronomers could be remembered as the first evidence that reality is far more vast, complex, and interconnected than anyone had dared to imagine. As we continue to decode the messages written in ancient starlight, we might be simultaneously learning to participate more consciously in the cosmic conversation that spans the multiple levels of reality. The universe is not just something we study. It might be something we help to create through the very act of understanding. We began this journey with a single point of light in the cosmic darkness, a galaxy so distant and ancient that it challenged everything we thought we knew about the universe's earliest chapters. Jade's GS Z14-0, shining across 13.5 billion years of space and time, became our gateway into mysteries that stretch from the quantum realm to infinite cosmic hierarchies. What started as an astronomical discovery evolved into questions about the very nature of reality itself. The galaxy that was supposed to be impossible turned out to be just the beginning. Its brightness without a central black hole. Its sophisticated chemistry appearing impossibly early. Its membership in a growing population of ancient cosmic giants all pointed toward a universe far more dynamic and interconnected than our theories had predicted. Each revelation built upon the last. Missing supermassive black holes led to questions about feedback mechanisms. Rapid chemical evolution challenged our understanding of stellar life cycles. The abundance of bright early galaxies suggested that dark matter and cosmic structure formation operated differently than we assume. But perhaps most profound of all was the growing evidence that galaxies across vast distances rotate in coordinated patterns, as if responding to some universal organizing principle that extends beyond local gravitational interactions. This cosmic choreography opened the door to the most radical possibility of all that our entire universe exists within a black hole in a larger parent cosmos. The implications cascade through every aspect of our understanding. If universes reproduce through black hole formation, then consciousness might play a fundamental role in cosmic evolution. The fine-tuning of physical constants could reflect an inheritance from successful parent universes. The rapid formation of early galaxies could express organizational templates encoded during our cosmic birth. We might inhabit not a unique, isolated universe, but one branch of an infinite tree of nested realities, each level contributing to a cosmic conversation that spans scales from the quantum to the infinite. Our scientific observations, our technological achievements, our very existence as conscious beings could be participating in information processing that operates across multiple levels of this vast hierarchy. The ancient galaxies discovered by Webb represent more than distant stellar nurseries. They are messengers from our cosmic dawn, carrying encoded information about our universe's ancestry and its place in the larger scheme of reality. Each photon that traveled billions of years to reach our telescopes might be part of a cosmic communication network that connects nested universes across infinite scales. As we stand on the threshold of even greater discoveries, we face a choice about how to interpret the evidence. We can cling to models that treat our universe as an isolated system, explaining away each anomaly with increasingly complex theoretical patches. Or we can embrace the possibility that reality is far stranger, more beautiful, and more interconnected than we ever imagined. The universe is not just something we study. It might be something we help to create through the very act of understanding. The endless frontier of cosmic discovery stretches ahead, promising revelations that could transform not just astronomy, but our entire conception of what it means to exist in a reality that may be infinite in its depth, complexity, and wonder.